Good morning to all the colleagues, juniors and seniors into the CME on the AI and machine learning in cardiac anesthesia. So welcome to all of you. So basically AI and MI we are already using in cardiac anesthesia. We are using and we were going to use in the near future also. So it's becoming increasingly pervasive in the healthcare system, the artificial intelligence and the machine learning. So with the uses, there is a risk always associated with the AI, artificial intelligence. So risk is basically for the healthcare administrator, clinician, and the healthcare provider. So it's our responsibility is to frame a safety network for the proper clinical implementation of the AI and machine learning. So in today's CME, we are going to cover all the topics like what are the uses of AI in cardiac anesthesia, what are the medical legal implications of this. As I told you, we have to develop a very safety framework in the healthcare setting for the clinician and the healthcare administrator for the safe implementation of the AI and machine learning. So without any delay, I think we should proceed. So handing over the dais to Dr. Mona Lisa. Thank you.
Respected seniors, esteemed colleagues, and dear friends, a very warm good morning to all of you. So, on behalf of IACTA West Bengal chapter, it's my privilege to welcome you all to today's academic gathering on the rise of artificial intelligence, the role of cardiac anesthesia. So we live in an era where the technology is not just supporting medicine, but it is transforming the total medicine practice. The artificial intelligence once was a subject of curiosity is now emerging as a valuable partner in our operating rooms, ICUs, research domains. So, from predicting the hemodynamic stability to guiding intraoperative decision making, AI holds promise to enhance safety, precision, and outcomes of our patients. So, however, with the every new advancements comes the responsibility. The responsibility to understand it deeply, apply it judicially, and uphold the human touch that lies at the heart of our profession. Today's session brings together some of the finest minds in this evolving field who will guide us through the science, the potential, and the ethical considerations of AI in cardiac anesthesia. I sincerely thank each of you for taking the time to be here. I hope that our discussion today will not only expand our knowledge, but also inspire us to embrace the innovation while staying rooted in the patient-centered cure. With that, let us begin our journey into this exciting and thought-provoking topic. The first speaker will be Mr. Chirag Maheshwari. He holds a BTech in Mathematics and Computing and an MS in Computer Science. His career has spanned some of the most exciting intersection of technology and the domain expertise, beginning as a software engineer at Adobe Systems and moving into machine learning research and engineering roles across the healthcare and finance. His work at the cutting edge of AI applications in radiology, pathology, and now financial technology, serving as a senior ML engineer and technical lead. Beyond his professional work, he shares his insight through his platform, digital-madness.in. So today he brings his deep technical expertise and cross-domain perspective to our seminar that is on AI in anesthesia. So we'll start our session with Mr. Chirag Maheshwari. Sir, up to you.
Thank you, Doctor. I'll start sharing my screen. I think that would be. I see. I don't have permission to share. Sorry.
Allow. You have to allow the sharing. Sharing is not turned on. Ah. 1 second, sir.
No problem.
You also have to, I think, allow this sharing because it's something that it has been allowed. Screen sharing has been allowed, sir. You can start the sharing of the screen now.
I think I just sent a request. Okay. Okay, now it's working. I'll get started. Thank you.
Thank you, sir.
Yeah, I hope everyone can see my screen. So, hi, I'm Chirag. Morning, everyone. So, I'll be talking about artificial intelligence in healthcare, and mostly about artificial intelligence and like how it's evolved, how how it impacts healthcare, and basically kind of the overall ecosystem of healthcare, and hopefully it's impacting anesthesia as well. So a brief introduction. So doctor has already given me about me, so I won't bore you with the details here. I'll move on to goals of the talk. First of all, I want everyone in this room probably hopefully to understand like what is AI, why how it applies to anesthesia and overall ecosystem of healthcare. And hopefully by the end of it, you'll be acquainted by the different terms used in artificial intelligence and what are the different techniques used and different even different mechanisms on how we debug or develop those. So, first of all, what is artificial intelligence? It's a branch of computer science, and it's dedicated to creating systems that can perceive, reason, plan, learn, and make decisions, much like how we humans do. And if you look at it as a whole, there's these automated systems can be very simple by let's say your blood pressure monitor. That's a very simple automated system. And on the other end of the spectrum is artificial general intelligence, which I think if you've heard of, it's basically this somewhat this mythical land that you given any task, you will be able to perform it without any supervision. But how I see this is we are actually here somewhere in the middle, which is artificial specific intelligence. That means we in with neural networks, with machine learning, with or how people call it artificial intelligence, we are able to achieve certain very specific tasks in a very in very specific environments very well. And that's where these systems come in play and are able to help humans to make faster decisions and even like provide any kind of decision support in healthcare. So, going over a brief history of artificial intelligence, the whole field actually spans like hundreds of years back. We in 19 around actually coined this term artificial intelligence, and it was previously called known as cybernetics. But for a period of time, a lot of attempts were made with symbolic AI, and along the time there were AI winters where we had limited computing or tighter funding. Then some techniques kind of started to evolve, which were known as expert systems. Expert systems are basically where you are able to encode every specific information in these systems, and then you're able to take decisions. For example, if you're if you want the computer to play a game of chess, then you want to encode each piece of information like that. Given chess positions, I will make this move, or I will make this move, and that will be the best move. But as you can see, these systems are hard to scale and grow. Why? Because you can't really encode each and every position. There are the number of positions on chessboard are infinite, or basically more than the number of atoms. So it's hard to encode all of those. And these we started to see fallibility in some of these systems. But at some point of time, there's some systems started to work. Some as computing started to grow, data started to grow, and there is one field that started to show a lot of promise, which is called deep learning. So from 2012 to present, I would call this the era of deep learning, where we saw a network called AlexNet achieve breakthrough performance in image recognition. And as soon as we saw that, like a lot of money and research continued to start to pour into this field. And along the time, around 2019, we saw a breakthrough performance on natural language processing as well. And at some point, OpenAI released the ChatGPT, and it came into public, AI came into public conscience. So first of all, what is artificial intelligence, machine learning, neural networks, and like how do I differentiate between those, right? So artificial intelligence is this whole field where we want the system to perceive, think, and actually decide on a basis. But machine learning is a small subset of this field where we create algorithms such that machine can actually learn instead of we providing each and every kind of information to them. And there are many techniques in this field, which are like linear logistic regression, k-means, support vector machine, principal component analysis, and they do different things, which we'll come to if we get time. And then there's a subfield, if you look at, which is neural networks, which are even powerful machines, and they are able to do much better pattern recognition. And and the very end of the spectrum, when you increase the power and the size of the neural networks, we call that is known as deep learning. And there are many networks in this domain, which are known as convolutional neural networks, recurrent neural networks, GAN, which is generative adversarial networks, and DBNs, which are deep belief networks. So what has changed, like kind of going from here, like which we call as symbolic AI, to era of deep learning, right? So what has changed is we came from these rule-based systems that we given an input, we hand design the program, and we provide that this would be the output. Then we move to a classical machine learning, which is linear logistic regression, support vector, where we give the input, but we design certain features. For example, if we're trying to find cat in an image, we encode, oh, these are all the lines, these are all the edges you have to look for. This is a tail you have to look for. There are 4 legs you need to look for. There is a specific face and eyes you have to look for. So those are called hand design features. And from those hand design features, you can create these mappings of features to certain outputs. And then we go up the stack and make it even more abstract is when we call it representation learning, where we, instead of actually hand designing features, let the computer design the features which will make this mapping from input to output even better. And 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 the machine would be able to kind of encode the information in input to be easily be able to map it to the output. And as you go along the spectrum, more and more, like if you add more and more more and more layers, you start to have like these kind of going from simple features to more abstract features, and then finally from these mapping of features to the output. And as we see that there has so many algorithms that have been created in this period, in this field. And this is something we see not just in algorithms, there has been an increase in computation. What I mean by that is like looking from kind of like 1950 to 2020 and like recently 2025, we see computation growing from like 0.001 petaflops to 110 billion petaflops. And each line is representing an 100x improvement in petaflops. And when you look at that means your computer is doing billions and billions of multiplications to actually give you an answer. And this improvement has caused a lot of breakthroughs in models like Transformer, AlexNet, AlphaGo Zero, AlphaFold, and just between this period, we've seen a immense rise in computation. Computation algorithms alone don't work. They need data to actually empower these models. What does that mean? We Any model needs to learn from data, and it's in the past 10, 15 years, the digitization of data has increased a lot. So we've gone from maybe even 0 zettabytes to generating 200 zettabytes, and zettabytes are basically hundreds, like thousands of terabytes, or like thousands of petabytes actually. So 1,000 into 1,000 a terabyte. So like even your small hard drive is can't hold this much amount of data. So we've kind of gone from creating this so much amount of data every period of time, that some of this, when come together, all the computation, the data, and algorithms, they have improved our capabilities in these models. And so if you look at this graph from Our World in Data, it's a really good platform to kind of look at how our world is doing in terms of different things. You can see as going from 1998 to 2023, we have gotten so much better in so many different domains, which is reading comprehension, image recognition, language understanding, language interpretation, handwriting recognition, and we've surpassed this human performance as the benchmark, like human performance benchmark. And if anybody follows like International Mathematics Olympiad or these like every year we kind of have these IIT exams itself, which is one of the hardest exams, and these models have been able to actually even answer these tasks or be able to win gold medal at IMO. So the capabilities has shown a breakthrough. So as we can see, there's a good rise of artificial intelligence and like learning what it means and how it performs or what it does and how it does what it does. It's very important. So to kind of come back to the theoretical framework of what happens is, first of all, you have data and you have observed ground truth. So for example, if you're doing image recognition, that is, let's say you're doing a very small example of finding cats versus dogs in an image, you want image like a lot of images of the observed data and observed ground truth, which what each image has, like does it has a cat or does it have a dog, which you construct in a training and a testing data set. Training data set is which will be used for kind of to create the train the model, and testing data set is when we take this trained model and actually test it on this same data set to figure out how it actually has it gotten better or not. And one of the main training algorithms we use is called backpropagation. Backpropagation means we uh, we take an image, we pass it through this network, this model, and actually predict how it's doing. If it's doing well, we slightly change the weights of the model such that it gives us the right answer next time if we give the same example. And that's what backpropagation does. It slightly changes the weights to improve the model or the neural network to give us a trained model. And we can do this in a very like a long cycle, going through the data many times until the trained model is doing really well on the training data set. And then we finally test it on the testing data set. So how do we test it on the testing data set? That is called inference, or inference means whenever we see a new observed data, we pass it through the trained model and it should give us predictions. So this is called inference stage. But what does a neural network really looks like, and kind of like what happens in propagation? Neural network, as the name suggests, it's actually it's a loose interpretation of a neuron in our brains. We have these dendrites, which send these small electrical signals through our brains and pass it down the axon and pass it to other neurons. And something similar we do in a neural network. And we get these inputs, which is an image. In an image, for example, the input would be the pixel values of each pixel values, and that can be provided here. And then you take a matrix of weights, multiply it with as a linear operation, so which gives a summation from weights into the input with a small bias, and goes through a nonlinear activation function. What that nonlinear activation function is somewhat what a neuron actually also do, where given certain signals from all the dendrites, it decides how much of the electrical signal it wants to pass it through the axon terminals, and something the nonlinear activation function do as well. And there's a common function called ReLU, which is and leaky ReLU, which basically says if the sum plus this bias is actually greater than 0, then we activate this value. Otherwise, it's set out to 0. And when you take this neuron and actually connect it in multiple layers across, you get this big neural network where you have these inputs, you have this weight matrix across multiple neurons, and then so each of this dot is a different neuron, and then you pass this information collected here to other neurons, and you kind of continue to do that until you get an output. But this is a very rudimentary kind of architecture for a neural network. And for different types of problems, you require actually different kind of neural networks as well. Like the same neural network might not work for a different problem, although like lately these large language models, which you see in ChatGPT and all of those, are much more multimodal. That means they can work with a lot of different types of data more easily. But in most cases, you tend to have a specific model for a specific problem. And the same with neural networks, that certain neural networks work really well for certain problems and others don't. For example, image recognition, you have this input of zebra, and you go through this convolution. So this convolution kernel goes through this small patch of the image and actually calculates the same weights as we were talking about, these linear weights, across this whole kernel and create this small feature. And you do this thousands and millions of times across these different layers, pooling layers, and you finally get this flattened layer of features. So these are called high level features of the image. And then you pass it through a fully connected layer to finally give you an output of, like, is it a horse, and sub probability. And when you have these probabilities, you can pass it through a softmax activation function to actually tell you that this isn't actually an horse, or this isn't actually a zebra. As you can see, the probability of it being zebra is the highest when it has gone through the whole image across these different layers. We can conclude that this is a zebra. And large language models actually use an architecture called transformer architecture. And this is an example of a transformer architecture. It's very hard to kind of go like really in detail. That might like take like a whole 1 hour lecture of its own. But as you can see, this is the convolutional neural networks, and this when we get to this transformer model, this small multi-head attention is a big layer of matrix multiplication in a specific format, which goes through and add a normalization layer, then a feed forward layer. A feed forward layer is something similar here, and then you kind of continue to do that across multiple layers with the same at the same time also encode the position of each information. For example, this patch was at a position 1 or position 2 or position 3, as a positional encoding, and which gives you these output probabilities, and which can help you finally just give you an answer of how ChatGPT does that, right? Going from text, going from a loose set of words, and getting like again giving you these loose set of words with these output probabilities. So whenever you see like the next word is X, it's what it's saying, like the next highest probable word is actually X. Now, as we talked about the trained model, there's a certain aspect of which we forget about is there are other things as well. Like what was the observed data? What is like how can you how or what type of ground truth data you can collect, and what training algorithm you can use. Based on that, there are different types of machine learning algorithms which have been created, and they are largely or loosely categorized into these 4 categories, which is called supervised, semi-supervised, unsupervised, and reinforcement learning. So in a supervised environment, it means that for each and every data point you have, you also have a label. So for every cat and dog image, you also have a label that this is a dog, this is a cat, and so that you're able to do this whole algorithm on a supervised basis, or have every information you need to test and evaluate. But there are semi-supervised techniques, which means you have only a certain amount of labeled data, and everything else is just images, or everything else is unlabeled. That is, you have the input data, but you don't really have the labels for it. And when you combine this as in the spectrum of try to learn certain patterns from the unlabeled data, and fine tune the model on the small portion label, that is semi-supervised learning. And this is very common lately to use semi-supervised learning, because most of the label you have or any company kind of can collect is unlabeled data, and only a small portion is available as labeled data, mostly because of its cost and the hardness of collecting such data. Then you have these unsupervised techniques as well, where let's say you don't have any label data. What can you do? You can't really make any prediction, but you can create stratifications. You can find patterns and clusters of common information, and group patients in these based on these anesthetic response. So that is called unsupervised learning. And common techniques in this are k-means clustering, and contrastive training. So there are many techniques in this unsupervised category. Then you have reinforcement learning, where the signal is not really a label, but a feedback from an action. So this is a very common technique used in robotics, where the agent or the robot takes an action, and after a certain point of certain sequence of actions, it might get a feedback that, hey, like you did this right or you did this wrong. For example, if I'm trying to train a robot to play a small video game for me, uh, it might need to perform certain actions, and finally like the feedback or the reward is if the model or the robot actually won the game or not. And that's a very sparse feedback. So reinforcement learning is really hard to implement, because you're kind of learning from these sparse feedbacks over very large time ranges. The main goal of such cases is, like, we want to learn optimal actions, what action one needs to do based on a given situation. And I've given certain examples what in anesthesia. I'm not the biggest I'm not an expert in anesthesia, so I'll let that be the judge of that. But for example, in supervised learning, kind of predicting hypotension from vitals, I would say categorize as supervised learning. If you have certain like labor risks with a lot of monitor data, that would fall into semi-supervised learning. And then if you have just that how these patients have responded to certain anesthetic drugs, then you can use these unsupervised techniques on how they have performed. And these reinforcement learning in action, like so closed loop anesthetic dosing, that you have you're dosing, giving a certain dose and checking how the vitals of the patient is moving. Now coming to ML in healthcare in terms of actually implementation wise, right? These are very complex techniques and require a very complex technology stack to work as well. First of all, you need a lot of data, right? And when you have a lot of data, you need a way to store all of that data. And you need a way to make that data PII, or basically remove all the personally identifiable information, get some consent from the patient that your data is being collected. So to create the systems and regulations around it, you need a lot of infrastructure just for that. Then on top of, once you have this data, you need to be able to do feature engineering and modeling. Feature engineering basically means like taking an image, be able to convert it into pixels, convert it into in a format which a model can understand and ingest, and finally be able to even store that. And then then you need to implement a lot of these algorithms, then do to actually be able to train these models, and even create some sort of explainability, which is known as XAI as short. So explainability in these models to such that we can create some trust and accountability in the predictions as well. Then you need a lot of infrastructure for making sure the models are actually doing, making sure the models are doing well. Are they being versioned? Like what kind of improvements are we seeing from version to version? Making sure the data is being processed correctly, and then being labeled correctly, and then get all the compute infrastructure like GPUs and CPUs, and be able to take this model, package it, and deploy it in anywhere possible. For example, in medical devices, or or maybe in medical watches, or these, or in any kind of device you might want to put this algorithm into. And it's not just enough to actually deploy this model, right? You will want to monitor and observe the model on top of it. So there's technology to be implemented there to actually get the to monitor how the model is really doing, get the feedback in terms of how the model is the model performing well or not, and in what cases not performing well and can be improved. Then there's so many safety, security, and compliance required with data and these model development, that you have to create the infrastructure to make sure any practices that go into model development are compliant with all the medical regulations. So we've talked about so many different things, like, but why like ML or AI is like healthcare is a perfect application for AI and ML. First of all, healthcare is data rich. It generates vast and diverse amount of data. It generates structured data from labs and vital, unstructured data from clinical notes, and a lot of physiological data. Like even my watch kind of keeps track of my heartbeat all the time, or like how my VO2 is doing. So there's a lot of time synchronized physiological data. And these machines are basically pattern recognition at scale, and which can perform multivariable pattern recognition, and be able to find, maybe like even count cells in pathology images, or from and take genomic imaging data together and be able to give an answer based on so much amount of data. Then at the same time, what it does, it helps you to be fast, precise, and personalized. What does that mean? First of all, clinical decisions a lot of times need to be made in seconds, not in days, not in weeks. So you want these things to be fast. and computers, as we know, are fast, right? So these models help you to make faster decisions given so much amount of data. Then reducing intra-physician variability, where if you go to one physician, they might have a different opinion of something. If you go to other physician, you might have a different opinion. And this inter-physician variability causes a lot of confusion for patients, and these models, which try to find patterns across diverse amount of data, can reduce this intra-physician variability. And then because they can ingest this amount of data, they can be personalized based on the specific needs of the patient. They can be personalized to make sure they are given the best care and they need based on the condition the patient has. And looking at a few win stories of ML, this is something I've also worked on. Is let's say you have this H&E image of tissue or melanoma cancer, and what these models can do is basically find each and every cancer cell and each and every macrophages, all the immune cells or the tissue cells, and kind of like which helps you do very precise computation on how much cancer is there, or how much immune cells are actually attacking the cancer cells, and which generally is called like tumor microenvironment. But these models are really good at actually finding these. And there's another story of looking at a mammography of a breast. They are able to find these malignant, or kind of like, or maybe even finding these benign pieces of or cluster of cells in a mammography. And if you look at another example of computational tomography, or like a CT image, they're able to segment based on similarly to a manual segmentation. Almost perfect, not exactly the same, but that's the fallibility of some of these models, but they come very close. Now coming back to like kind of how it applies to anesthesia, I'm not an expert, but happy to try to give some information on the different times anesthesia is involved in a surgery, which is the preoperative, intraoperative, and postoperative. It can be used in risk stratification initially, if a patient should be given like more like what kind of precautions one needs to take based on the surgical risk. If a patient is high risk, then it needs to be prepared accordingly. And during actually a surgery, you can do real-time monitoring and set up alarms, and be able to early detect if anything bad is happening or risky is happening. And in some cases, also provide or automate drug dosing in these closed loop system. And at the end of the day, when the patient is done with the surgery, it can help with like how much, maybe even predict like how ICU stay length, there, like if there is going to be any complications, or be able to make the perfect plan for care plan for post-operative surgery. As I talked about these benefits, what ML brings, but or like anything, that there's no free lunch anywhere. Anything comes with a lot of challenges, and machine learning comes with a lot of challenges. One is cost, like infrastructures and systems for machine learning are costly and requires extensive expertise. The data quality and availability is hard. Like there's the way one hospital collects data can be very different from how other hospital collects data. So there can be broken interoperability between hospitals, which can cause lead to reduction in data diversity and harmonization. Then you have generalizability. Let's say you have created this model. It works great on the training data set. It works great on the testing data set, but we don't know how it does on the unseen data set and high stakes situations. So generalizability is a challenge, and constantly being tackled in this field. Then interpretability is a very important challenge, especially in healthcare, where explainability, these are very complex systems, and if you try to reduce a complex system in a very simple words, you lose a lot of details, you lose a lot of what even interpretability means at that point, like when such a complex system is making a decision, right? So model interpretability and explainability is hard, and oftentimes is one of the underfunded researches. And then integration, like let's say you have created this AI or you have these, how do you actually integrate this in clinical workflow? So that requires upskilling, updating equipments, updating our guidelines for the world and for the hospital. Then you have feedback and validation. So a lot of the times, like importance should be given not just by testing in these academic cases, but also in real world scenarios. So large scale clinical trials are required for validating any kind of efficacy, which can be costly in itself to perform. And then there's development of regulatory bodies in this context. Like I've mostly seen that regulatory bodies still haven't caught up with kind of all the progress that's going in the technology. Hopefully they do, but regulation is an important aspect of actually developing this technology with care in mind. And regulation is really important in that case. So, but like regulatory bodies are still catching up with it, like how the technology has progressed. Then bias and equity, that data might not be diverse, and that would exaggerate any kind of disparities between underrepresented groups. So that with these challenges, I'll close my talk, and thank you everyone. I'll stop sharing. I'll take any questions, but if we're running out of time, we can move on to next, and I'll take questions whenever we get time again.
Hello, can you hear me, sir?
Thank you. Yeah, thank you.
That was very elaborative. Thank you so much. That cleared our basics of what we are looking at when we are talking about AI. Sir, we like to take up questions. This session is actually a YouTube live streaming session. So we'll wait for 2 minutes for any questions if there are, and then we'll be proceeding. We'd like to have you with us throughout the session, sir, if possible. Thank you.
Thank you.
Thank you, sir. सर YouTube में देखिए कोई क्वेश्चन है कि सर YouTube वाले में कोई क्वेश्चन आया है कि लिंक में नहीं ना. So we are not looking at any question right now. Thank you so much, sir, for the presentation. We will be waiting for your next lecture. I'll now hand over the mic to Dr. Mona Lisa. Ma'am.
Thank you, Reshmi. Thank you, sir, for the excellent presentation and so much elaborate presentation. Actually, we actually don't know about so much details about this topic. And thank you, sir, for this enlightenment. And now we are moving to our next session, that is a session 2, AI-guided ventilator and anesthesia management, the closed-loop systems for titration, monitoring during cardiopulmonary bypass, awareness detection, and BIS automation by Dr. Shotajit Mishra. He's head of the department in cardiac anesthesiology in AIMS, Odisha. So we are starting his presentation now. Thank you. Thank you very much.
Good morning to everyone. And at the outset, I would like to thank Dr. Mona Lisa Datta and the West Bengal Act for inviting me to give this talk on closed loop systems for titration monitoring during CPV with awareness detection and this automation. I do not have any conflicts of interest to disclose. And how we're going to go through the talk in the next 20 minutes is I'll be discussing about what are the various closed loop systems, the advantages and disadvantages of closed loop systems for awareness monitoring. How do they impact patient outcomes during cardiac surgery? We'll look at some of the evidences, and then I'll round off by telling you the 3 laws of closed loop systems and a little bit about the role of artificial intelligence in closed loop titration. Now, if you look at it, automation is not a new thing. It's been around us for quite some time. We know that planes mostly fly on autopilot, and we also have driverless cars. And all this thing is done with an aim to reduce the stress on the operator so as to improve the overall experience. Similarly, automation has also been there in the form of closed loop systems in anesthesia for nearly more than 2 decades now. And basically, these are nothing but feedback and control systems. So there are 3 essential components. There's a sensor, there's a controller, and there's an activator. And using this, the anesthesiologist is able to titrate the systems. We have a number of systems that are used in anesthesia according to the closed loop principles. For example, we can titrate the output, that is the hypnotics, according to the patient variables. So the inputs for a closed loop hypnotic system would be the bispectral index or the entropy, which are the processed EEG, the heart rate, and the mean arterial pressure, and the output will be the anesthetic concentration. So if you look at the picture to the right, so the clinician basically sets the target on the feedback controller. So the target would be, say, for example, if it's the depth of anesthesia closed loop system, you would set a target bispectral index of 50 to 60, and then the system then monitors the actual BIS through the sensors and other variables also, such as the heart rate and the mean arterial pressure. And based on whether this actual BIS is equal to the target BIS or not, then the feedback controller then activates the therapy, which may be a bolus of propofol if the actual BIS is higher than the target BIS, or it can decrease the dose of propofol if the actual BIS is lower than the target BIS. So this is how a closed loop system works, and basically it eliminates the human interference from the system. So there are more than 18 closed loop systems that are used in anesthesia and critical care, and some of them are ventilation control. We know that there is automatic weaning of patients as they become more awake. There is weaning of patients. There's temperature control. There's hemodynamic control. There is fluid management. There's neuromuscular control, and there are even closed loop systems that try to control the analgesics based on the heart rate and the mean arterial pressure responses. When we look at the closed loop systems in cardiac surgery, there are certain advantages. For example, there may be less use of anesthetics. Patients have more hemodynamic stability as a result of that. There is a faster recovery, and all this thing leads to naturally lower costs. But the disadvantages would be that the CPV, during CPV, the physiology is altered. So many of the variables that are valid in patients who are undergoing non-cardiac surgery, like heart rate, mean arterial pressure, bispectral index, may not be so valid in the patient who is having an all pulsatile circulation and a hypothermic milieu. Many protocols are still in the research domain. For example, many of the hypnotic protocols using the newer drugs are also in the research domain. The devices are different and their performance is not standardized, and there's no robust evidence that this leads to any improvement in the long-term outcomes. So with this background, let us see when we use the bispectral index as an input variable, how does it perform in patients who are undergoing cardiac surgery with hypothermic CPV? So there was this paper that looked at the changes in the bispectral index values under cardiopulmonary bypass, and what they found is that immediately on institution of bypass, the CPV, the bispectral index values dropped significantly from pre-CPV values. So they came down to 25 from around 40 to 60. And the authors postulated that the decrease in the bispectral index could be due to various reasons such as hypothermia, hemodilution, or an oxygen poor prime perfusing the brain. So this is one of the problems in using bispectral index as an input variable for closed loop anesthesia systems that deliver hypnotics. Let us look at some more evidence whether the bispectral index monitoring is useful on patients on cardiopulmonary bypass. So this was a study where they looked at 30 patients who were undergoing various types of cardiac surgery, either valve replacement or coronary artery disease or coronary artery bypass grafting surgery. And the patients received isoflurane anesthesia and boluses of morphine. In the study group, the anesthetic depth was controlled using the bispectral index and clinical variables. And in the control group, the bispectral index monitor was hidden from the anesthesiologist. So what they found is that the patients in the study group had significantly less hypertension and tachycardia than those in the control group, where the clinical parameters were used to manage the patient. And there were other benefits also. For example, the time to recovery of consciousness was less in the study group as compared to the control group. And in the control group, the bispectral index significantly rose significantly during the time of institution and termination of cardiopulmonary bypass, probably due to dilution of the anesthetics. Therefore, it can be concluded that the bispectral index monitoring is useful despite its limitations in patients who are undergoing cardiac surgery on CPB. So let us also look at what is the agreement between the various depth of anesthesia monitors on cardiopulmonary bypass, because not everybody may be using a bispectral index monitor. Some of us may be using an entropy monitor for monitoring the depth of anesthesia. So here, this small study, they looked at the correlation and agreement between the bispectral index and the state entropy, which measures the depth of anesthesia during hypothermic cardiopulmonary bypass. And what they found was, essentially, they found that the BIS and the entropy values, there's good agreement as long as the patients were normothermic. But the moment the patients became hypothermic, BIS was okay, but entropy was not. Therefore, if one cannot interchange the monitors between a case or in the same patient. So if we are using any one monitor, we have to go with that monitor and follow the trend on that monitor rather than using monitors interchangeably. Again, anesthetic requirement. Is it different in patients who are hypothermic versus normothermic? Again, research in patients who were undergoing cardiac surgery shows there were around 50 patients who were undergoing cardiac surgery on cardiopulmonary bypass. They were divided into two groups. In one group, the patients had hypothermic CPB, meaning the core temperature was taken to less than 30 degrees. And in the other group, the core temperature was maintained above 35 degrees. And in both the groups, patients received propofol, and the target bispectral index was around 50 within a deviation of plus minus 10. Though what these authors found was that CPB significantly reduced the propofol requirement in both arms of the study, but the reduction was more profound in the hypothermic group, and the BIS remained constant during the normothermic group, but significantly declined during the hypothermic group as a result of the hypothermia. So this is also something that is to be kept in mind, that the moment we go on hypothermic CPB, the anesthetic requirement itself will come down as a result of the institution of hypothermia. And therefore, that also is going to play a role in how the closed loop systems perform during hypothermia. So this was the first proof of study about the closed loop. So after looking at the limitations of the bispectral index or the entropy monitoring as an input variable, now let us look at the closed loop systems, how valid they are during cardiopulmonary bypass. So this was one of the first proof of concept studies looking at the closed loop control of anesthesia, and they used the input variable was the bispectral index, and the patients were undergoing open heart surgery. So this was reported around 2009. It was a small study. They looked at just around 34 patients in various ASA grades, and these patients were undergoing cardiac surgery under hypothermic CPB. What the authors found is the closed loop system was functional during 96% of the anesthesia duration. That's nearly 100% of the time. And the BIS was also maintained within a target range during 86% of the set BIS during this time. So essentially what they found is that the closed loop controlled delivery of anesthetics is feasible when we are using BIS as an input variable. And this may be even useful in patients who are undergoing cardiac surgery under hypothermic CPB. Pretty much the same thing in another study, the same authors, they looked at the performance of the closed loop anesthesia delivery system using the bispectral index. And what they found is that the closed anesthetic delivery system with their patented device led to lower induction doses of propofol with less overshoot of the target BIS. And the closed loop system also was able to maintain the BIS within a range of 10 at the set target for a longer time during the maintenance phase of anesthesia, and there were smaller amounts of the anesthetic agent used, which led to faster recovery. More importantly, the maneuvers to attempts to manual delivery of propofol led the anesthetist to change the dose of propofol at least 30 times in the manual group to adjust the BIS. So therefore, the operator interference or the operator effort is taken away in the closed loop system. Again, the question that begets itself is, how does the closed loop system perform in patients with severe LV dysfunction? The same group of authors, and most of the work in the closed loop anesthesia delivery system has been done by Professor G.D. Puri. So one must mention his contribution in this domain. So again, the same group of authors, they looked at the anesthetic depth using closed loop anesthesia delivery systems versus a TCI system in patients with moderate to left ventricular systolic dysfunction. And what they found is that the BIS remained within the target BIS for a greater time in the closed loop anesthesia delivery system as compared to the TCI system. Now, the TCI system is basically, it targets the plasma concentration. So there is no input variable using the bispectral index or the hemodynamic parameters, whereas the closed loop system uses the various input variables and modifies the dose of the drug. So that's essentially the difference between the TCI system and the closed loop anesthesia systems. Both use TIVA, but this is the essential difference in the functioning. So what they found is that not only was the BIS maintained for a greater time within the target BIS in the closed loop anesthesia delivery system as compared to the TCI system in patients with LV dysfunction, also the total propofol consumption was significantly less in the closed loop system. Therefore, the closed loop system performs better than the TCI system in patients with severe LV dysfunction. How about pediatric patients? Most of the evidence that I had shown you was in adult patients. Again, it's no surprise that the same group of authors, Professor Puri et al., they evaluated the performance of the closed loop anesthesia delivery system for in pediatric cardiac surgery using propofol. And what they found is that they divided it into two groups. One is the closed loop system and the other is the manual group. The BIS was kept within the target BIS and the intraoperative hemodynamic similarity was similar between the two groups. But in the closed loop system, the induction dose of propofol was significantly less than in the manual group. There was less overshoot of BIS during the induction, and the total propofol in the off CPP period was significantly less in the closed loop system with a lower requirement of vasopressors. Therefore, even in pediatric cardiac surgery, the closed loop system performs better than the manual system. So, is the closed loop system only for TIVA, or whether the volatile anesthetics can also be used with the closed loop system? So, again, no surprise that the same group of authors have looked at whether the volatile anesthetics can be used, can be administered using a closed loop system. And what they found is that they designed an indigenous system, that is the improved anesthetic agent delivery system, which is a modification of the TIVA-based system, and this was designed to deliver the inhalational anesthetics and propofol through the closed loop system. Again, the input variable was the bispectral index, and what they found was that the volatile anesthetic closed loop delivery system was able to maintain the bispectral index within the target BIS for a longer period as compared to the manual group, and the overall performance, precision, etc., were significantly better in the closed loop volatile anesthetic system. And therefore it's feasible and safe to use the inhalational anesthetic delivery through the closed loops control. And how it works is basically it just adjusts the fresh gas flows to maintain the end tidal MAC and the bispectral index within the desired ranges. So let us sum it up with a review, with looking at a review. This was a recent review that looked at the hemodynamic stability of closed loop anesthesia systems. Now, this is not specific to cardiac surgery, but they included all studies where the closed loop anesthesia delivery systems were used. And what they found is that there is better hemodynamic control where the closed loop systems are used. And the BIS is also within the more time within the target range when the closed loop systems are used as compared to the manual systems. So before we end, presentation on the closed loop system, we must understand there are three laws for the closed loop system. The first law is the first, do no harm. So basically the closed loop system should have safety overrides, and the best example of that is the anesthesia machines have a fail-safe mechanism like the oxygen nitrous interlinking system, where we cannot deliver a hypoxic mixture to the patient. It will just cut off the delivery of the nitrous in case the oxygen falls below 30%. So similarly, the closed loop systems should also have safety overrides. So in case that there is a problem with the feedback in the system, they should stop in the closed loop mode and automatically ask the operator to go into the manual mode. Again, the companies must be transparent. They should clearly lay down the assumptions and the algorithms to the operator when prompting the anesthesiologist to use the closed loop system. We should know what functions are, how the assumptions or the algorithms are designed. That must be clear to us so that we can better understand how the system works. And it should reduce the cognitive workload. The system should not demand excessive monitoring by the anesthesiologist. Imagine if we are having to continuously monitor the closed loop system, then it really doesn't add to our advantage. Rather, it further acts as a deterrent to the other cognitive tasks that we can perform, because in the busy cardiac surgery operating rooms, the cardiac anesthesiologist has to look at the echo, he has to look at the hemodynamics, he or she have to look at the anticoagulations, and so on and so forth. So if we have a hypnotic system, if we have a muscle relaxation, if we have the other things as part of the closed loop system, then we should not be excessively monitoring the closed loop system. That would defeat the whole purpose of a closed loop system. And finally, how the future is going to be integrated. So there's going to be more use of AI with the closed loop systems. AI basically is a machine learning or a deep learning model where the system improves itself by seeing the performance of the closed loop systems and improving the performance. So it will basically look at all the errors the closed loop system is making, and it will sort of improve that, improve the performance of the system so as to minimize the error and make it more efficient. So for example, the deep learning models, they work on the various neural inputs, network inputs, and the network inputs may be the performance, the time the device is able to keep the bits in the appropriate ranges, the other performance characteristics of the device, and so on and so forth, and looks at how it can improve these errors through the hidden layer connections. And finally, through the network output, it refines the overall performance of the machine. So finally, with complete automation, can we have the luxury of becoming something like this? So we just come to our workplace, just lie down on the sofa, put our legs up, start the closed loop systems and sleep off? Unlikely. It will be very, living in a fool's paradise if we think that this is going to be the future for anesthesiologists with complete automation. We'll still have to be involved and be more responsible. Just imagine that in our houses, we have all automation. We have the fridge, we have the washing machine, we have the dishwasher, we have the microwave, the vacuum cleaners. Does it mean that we have become redundant in the house? No, we still have to keep our house in order. Similarly, we still have to keep the OR and the patients in order. So with complete automation comes more responsibilities, and that is how the future is going to be. And with that, I would like to thank you for a very patient hearing, and I'll be happy to take any questions should there be any. Should they? Yeah, I can hear you. Thank you. Thank you. Yeah, Gravi, hi. I'm doing fine. How are you? The question is, no, so we don't have any experience with the closed loop systems. We are using the open loop systems. So we are using TCI systems, but the TCI systems basically work on a pharmacokinetic model and not necessarily on the patient inputs. In India, the most of the work the closed loop system has been done by PGI Chandigarh, Dr. Puri, and they have a commercial device also. But I'm not sure how many centers have but if you ask me that question, I don't think there's a very good adaptation of the closed loop delivery system in cardiac anesthesia practice, at least. Yeah. So am I audible now? Am I audible now?
Yeah, you are audible. Hello? No, I think some network issue is there. Okay. Anyway, it's a wonderful presentation, and thank you for answering. Okay, boss.
Thank you, sir. We now move on to the next topic of the day, a panel discussion.
After that excellent and so much elaborated
Yeah, am I audible
presentation.
now? Hello?
Hello? Hand mic. Hand mic. No. Session is next week. Sir, आप बात कर लीजिए.
Hello?
Sir, is Dr. Ravi is audible?
Hello? Oh. I think some network issue is there. So we are moving to our next session. Thank you, Dr. Satyajit, for nice presentation.
We are moving to our next session. That's a very interesting session. That is AI and perioperative echocardiography, which is one of the most important and most interesting thing in our cardiac anesthesia program. So we'll be discussing about the AI-assisted TE image recognition and measurements, real-time decision support in VAB surgeries, and the future of 3D and automated analysis in transesophageal echocardiography. So we are having our expert panelists with us. The moderator, Dr. Arup Ratan Maiti, who is a senior consultant cardiac anesthesia in Apollo Hospital, Kolkata, is one of the expert in this field, the TE and the perioperative echocardiography. So we have panelists, the expertise panelists, Dr. Shuddhadev Roy, Senior Cardiac Anesthesiologist, BM Villa Hospital. Shuddhadev, please come. Dr. Lini Srivastava, she is professor, associate professor in RG Kaur Medical College. Dr. Lini. Dr. Obhinandan, he is also a senior consultant cardiac anesthesiologist. Dr. Arnab Shamanto, our very new champ, very enthusiastic and very knowledgeable. So we begin with Dr. Arup. Please start the session. Thank you very much.
Thank you and good morning. It's wonderful to be here, and thanks Dr. Moralisa, Dr. Rovi, and all the West Bengal ACTA for giving this opportunity. As for the academic curriculum is concerned, it's going brilliant. So today we'll discuss we'll do a panel discussion on role of AI in echocardiography. And as Dr. Moralisa said, we have 4 panelists. Dr. Abhinandan Mandal, he's a consultant in Apollo Hospitals. Dr. Sudadev Roy, he's a consultant in BM Birdla Heart Research Center. It's a native institute, I think. And Dr. Arnav Samanto, who is again a consultant in BM Birdla Heart Research Institute, and Dr. Lenny Srivastava, who is the HOD of the RG Kaur Medical College. All of them are qualified echocardiographer, had a great experience in echocardiography. And so before I start the actual discussion, we have no conflict of interest, no financial disclosure, except I have used a couple of softwares of Philips, mitral valve, and Siemens software, and selectively used AI because it's an AI-based session. While searching through the literature, I searched plenty of literature and found a lot of recent articles, and while I'm showing these articles, that means the questions and answers and discussion will be influenced by whatever being written in these articles. And starting with this article published in June 2025, almost less than 2 months back, complete AI-enabled echocardiography interpretation with multitask deep learning that included 1.2 million echocardiographic videos from 32,265 TT studies and 24,000 patients. And they concluded an AI system can automate complete echocardiogram interpretation with high accuracy. So with this background from this study, we'll go to our panel discussion. And the questions I will ask in the sequence, like first will be Dr. Abhinandan. Abhinandan, what are the different methodologies that the echocardiographic machines use for the AI?
First of all, thank you very much for considering me as a panelist. So, in case of AI, there is first there is a machine learning, and beyond that there will be a neural networks, and beyond that, and the things we are using right now, that is a deep learning. So to make it very simple for our audience, to just make it you people understand that machine learning is just like a new medical student who is actually seeing any patients, and he or she keeps on categorize this patient according to whatever he or she has read in the textbooks. So he has not any whatever input they receive from the textbook, they try to put the patients into that scenario. So in case of neural networks, it's just like your day-to-day consultant. So, and your deep learning is just like your senior consultants. So just to make you people this understand, so in case of machine learning, we just give inputs to the patient, to the echocardiography machine. They know, we also give the particular rule, and we also feed them with the outputs. So the machine tells us whatever he or she, whatever it has learned from that rules, and whatever learned from that inputs and outputs. But it has no particularly learning from itself. In case of neural networks, there is a multiple connection. Just what do you mean by neural networks? Because it's just like your brain. There is a multiple layers of neurons. So they are interconnected with each other. So they can make their own decision. They don't only just consider whatever they have read in their textbooks. They also put something from the guidelines. They also take from their clinical acumen. All these things are included. And your deep learning, which is the most important thing right now in the echocardiography, it is just like your senior consultant. He also inputs here deep and all this huge experience with the patients, whatever he or she has seen for the past huge academic and career years. So these things are considered as a
Thank you. I liked your answer. It's really brilliant answer. Now coming to Dr. Suddhadev, what are the steps for deep learning? Abhinandan was talking about deep learning.
Yeah.
What are the steps for deep learning workflow in automated image analysis?
Yeah, so taking a cue from Abhinandan, what you're saying was absolutely right. So deep learning is actually a subset of the machine learning where it deals with a complex set of data. So it actually gets inspired or mimics the way the human brain functions and deals with a lot of complex data. So it has got inputs from the patient information, and then it has got some hidden layers where actually the processing and the weighting occurs. And then after that, there is the output or the provisional diagnosis or the treatment results in there. So initially, there is the dataset creation where there is the patient selection and the pathology and the proper finding of the images and the labeling of the images, which is kind of, again, part of the supervised learning in the machine learning phase that you can say. So that part is there. Then after that, there is the assessment of dataset where we have to take the statistical data, that is for building the reference range for the values of these different structures or different images. So that is required to set the outliers and the data that are outside the value, that to find out again the unsupervised areas. So that is again important. Next is the model development. We need to find out whether there are two main types of deep learning models. One is the continuous, one is the convolutional neural network, another is the recurrent neural network. So we have to find out which network will be useful for analyzing these type of images. Then there is the model assessment. We need to validate and assess the model, whether it is useful for that, and we need to modify those results accordingly. And there is the model validation that gives the final result and the provisional diagnosis upon which we can see whether there is any sort of treatment or modification that is required at that point of time.
That's an excellent elaborative answer. So basically, you want to stress that deep learning is very important for the neural machines. Thank you. Coming to Dr. Arnav, your first questions maybe. What are the different applications of artificial intelligence in the field of echocardiography?
Thank you, sir. I'd like to greet all my seniors, my colleagues, and my dear juniors. So, as we all know, machine learning models, they actually combine the echocardiographic data along with the clinical information that is provided, along with other test results. And ultimately, it formulates a predictive, a predictive profile by which it can actually enhance in the diagnosis, the therapeutic interventions, and the risk stratification of the patients. So AI, what actually it does is that AI takes raw data images or videos from the echo machine, and it automatically measures the functional and structural characteristics of the heart, as in case of echocardiography. So how it does it is that it actually has an automatic analytical ability to scan the echocardiographic image properly, which may be missed by the human eye. Subtle changes that occurs that we might miss. The experienced means this learning models will facilitate to identify those fallacies in the human error. So another important thing is that following this model training, we can actually apply this AI in several clinical scenarios, like for the diagnosis of structural and functional part of the heart, evaluation of the heart, and also we can diagnose specific diseases also. So what it does is that it also draws a ROC curve, as we can see. So this ROC curve actually helps to determine the risk predictive model to between a patient who has a condition from a patient who does not have that condition. So these are most of the applications that currently we are having.
Thank you very much, Arnav. This is a really, really nice answer. Going to Dr. Lini now. So actually continuing with the discussion what Arnav was doing, what are the potential clinical applications of AI in daily echocardiography practices to identify different disease states?
Good morning, everyone. Yeah, definitely AI plays a great role in diagnosing the different diseases via via echocardiography. So starting first with the coronary artery disease. So here, the systolic function can be assessed with the help of measurement of ejection fraction, where from a single 4-chamber image, the AI can deduce the ejection fraction via automated endocardial border detection. The diastolic function can be assessed with the help of the LA-LV strain. The regional wall motion abnormality, the ischemia, can also be detected and detected early through the AI. Then for the cardiomyopathies, there are different cardiomyopathies. For example, dilated cardiomyopathy can be detected via GLS. Then by measuring the tissue echogenicity, we can find out about the infiltrative cardiomyopathies. By measuring the thickness of wall, you can find out whether it's a HOCM or it's just a hypertrophy of the myocardium. Then for the cardiac masses, AI detects the mass size, exact location, and by the edge detection technology, it can also tell you whether it's a benign or a malignant sort of mass. And you can also use the AI for the long follow-up of the patient to find out the disease progression. Then comes the left ventricle hypertrophy etiology. So it can tell you whether it's due to hypertension, AS, or any other parameter, and it will also give the LV mass. And for the valvular heart disease, again, what is the pathology, what is the severity, and most importantly, if given with the 2D and the 3D data, AI can also tell you the exact anatomy of the valve that can help in the recent trending procedures like mitra clip or TAVR. So you can say that all these data we can get from the conventional echocardiography as well. But the difference is that the AI will give you this with better speed, better efficiency, accuracy, reproducibility, early detection, as well as it can integrate these data along with the comorbidity data of the patients, the genetic data of the patients, and can tell you much more about the patient, can help you make the decision what should be done for the treatment of this patient. So AI is faster and a step ahead than the conventional echocardiography.
Thank you. That's wonderful answer. As wonderful is the AI. I mean, the areas, if you see wherever we are like stuck or you're between dilemma, subtle changes of these difficult chronic diseases. So those areas, AI has a big role that I can see. Coming back to Abhinandan for your next question. So AI has been in huge nowadays in widespread in most of the machines. So how AI supports the echocardiography workflow? Does it help it anywhere?
Yes, actually the thing is that in the perioperative period, there is currently 30 views that we deal with in case according to your AAC guideline. But hardly in the perioperative setting, in that short span of time that we get, it is impossible to see each and every views. So, so we may miss lots of things in that time. So hardly we deal with maximum 3 to 4 functional views or whatever the patient's pathology is concerned. Suppose we are dealing with mitral regurgitation, we tend to just see only mitral valve. We tend to see only the LV. We tend to see only the LA.
Right.
But these things which we are not seeing, the machine is, the AI sees everything. It takes up the function of every pixel that it takes. So that is a major advantage of AI. And what it does, it does the post-processing part. So after image acquisition, it divides the heart into few segments, that which part is the atria, which part is the ventricle, which is the mitral valve. They just they just make it up on their own. And after that, they also classify the view, the which views we are dealing with. They see the omniplane angle, they see the depth of the TE probe that we are dealing with. So they see the structures that the machine sees. So they classify the views accordingly. And also they do the measurements, that the length of the leaflets and your coaptation length, all the things, all the your myocardium thickness, your LVIDD, your EF, everything, every calculation, including your strain analysis, your left atrium or other chamber quantification, all these things are done. Right. And according to that, they produce a report as well, whether we are dealing with a severe mitral regurgitation, whether it's a moderate, and they also help us to decide whether to delete or not, whether to do it surgically or we have to do it something else. They give a diagnosis for us also.
So in a summary, you mean to say that it reduces the workload of the echocardiographer?
Of course, sir. Because in a perioperative cardiac anesthesiologist period, he has to deal with multiple machines.
Yeah.
Not only he will do a TE, he's also having to do anesthesia. He have to maintain the hemodynamics. All those things they have to keep in mind.
Also for a transthoracic echocardiographer.
Yes, of course.
They're doing maybe one echocardiographer doing 50 or 100 studies a day.
Yes.
In that
yes.
case, AI
it is impossible to see each and every views. Though it is a possibility. This is evident that he or she will miss something.
Thank you very much. Coming to Dr. Sudhodev. So now, as we know what we do with AI, so can you just give an example, like compare between conventional measurement, like previously you used to do with a strain, and now you do with AI?
Yeah. So as we know that strain or the myocardial deformity, it's actually an indicator of a subtle ventricular dysfunction. Where what the machine does is it actually sees the deformity or the change in different ventricular segments. It divides the ventricle in myocardium into small segments and sees the change in every ventricular segment, the contraction in every beat. So what the conventional machine does is it actually takes the views, identifies the view chambers, and in case of the manually operated machines, we have to first select the chambers, and then we have to set the region of interest, select the endocardial borders, and select the speckles, the speckle tracking, or the different segments that that is designated as speckles. So that those need to be identified first and identified properly. Then we need to make the modifications as needed according to the different conditions, different positions of the ventricular muscles, wall, and everything. So by doing these things, ultimately the machine calculates the strain. So we have to do this for every view and for every image we have to select it. So this takes a lot of time. And all these things can be minimized. All these steps can be bypassed if the whole thing can be automated by the use of AI. So it makes it a one-click or a zero-click measurement of all these things. So obviously, it reduces the total examination time and the result giving output time a lot. Actually, one important study that came up in the Imaging journal in 2021, they studied about 200 patients for which they have studied the different echocardiographic parameters, and they have seen that the use of AI in strain imaging or overall ventricular functions, they have improved considerably the output and with the faster time, and they have considerably reduced the observer variability. So that was much reduced with the use of AI. So definitely it uses a lot.
Thank you. So you think it's fairly accurate because you have used it manually yourself?
Yeah.
The machine is giving
definitely, it's quite accurate.
So you can rely on that. Coming back to a question to Dr. Arnav, before that, probably I will also add to your answer, Dr. Sudha. This is a 2018 when I start first using the AI, and this is a mitral valve navigation software that is to give, because if you can remember, every point from the coaptation point, from the leaflet, from the annular point, I had to put myself in this software. And now That software has gone. Now the Philips AutoMP 3D, with a single click of the machine, absolutely does everything. So it's not even 7 years or maybe 5-6 years. The things are changing really fast. So like used to do strain previously, now single click, same thing with mitral, same thing with everything. Just to give an example. Dr. Arnav, so can you please summarize the strategies for the effective use of AI in echocardiography? Obviously, I mean, someone is new, anyone can't, this layman can't use echocardiography. So to use effectively, how, what are the strategies you will suggest?
So in order to use AI in echocardiography, novice operator needs to go through firstly a basic echocardiography training. That is the most important, because AI needs a good 2D image. Then only AI can actually function properly. So that is the foremost important thing. Secondly is mentorship. This is another very, very important thing, because inexperienced echocardiographers may not be able to get a good image acquisition, and it ultimately may lead to inaccuracies in measurements and diagnosis. Thirdly, another very important is operator skill and experience. This is a thing that we gain with doing echocardiography over the years, and also by applying AI from the outset also helps in the experience with dealing with AI echocardiography. So all these things are basically needed, and to get a good 2D image, that is the most important thing that we need. So after that, then only the AI will help us in a good way, actually, sir.
So now if you can see this schematic diagram, any novice, any medical student can get an AI tool in your hand, but obviously there should be some license or something for their use. Otherwise, I mean, for inexperienced or beginner or even novices, they should always be guided by an experienced thing. Okay, and it significantly reduces the patient waiting time. That's a very good thing of AI. And Dr. Lini, so at which point the AI bypasses the manual echocardiography? Somewhere there is no AI doing a manual echocardiography, and somewhere there is a AI with the machine. At which point the AI bypasses and slashes the time and gives the extra advantage?
So as you can see from this slide, the echocardiographic imaging is being done by the physician and the data has been acquired. Now, there can be two ways. Either this data is interpreted by an expert, like the traditional image echocardiography does, or we can acquire the data, give it to the AI for processing. So AI quickly, within a splits of second, will give you echocardiographic report with all the nitty-gritty facts. You can AI can also diagnose the cardiac condition at the same time, and if fed with the other data, the demographic data of the patients, the comorbidity data, etc., can also help you to make a holistic decision about the treatment. So this point, that is the processing of the data, the interpretation, the diagnosis, and the idea for the treatment, this is the point where the AI surpasses a traditional echocardiography, the time.
Thank you.
And one step ahead.
Brilliant. Dr. Abhinandan, so we have now so far talked about all the advantages, good things about the AI. Is there anything like any limitations of AI in echocardiography?
The major vendors which are working on echocardiography and perioperative echocardiography, the machines that we are using, those are based on mostly on Western population. That we have to remember. That they are not, they have not been the study done yet in our Indian population. Number one. Number two, there is a major concern regarding its use in the congenital heart disease patients, because congenital heart disease is a huge spectrum of patient. The anatomy can be anything from everything. So that is a major limitation for your AI to use. And there is also that you have mentioned before also, there should be some regulations, and there should be some medical legal aspects for this reports that the AI is generating, whether it is valuable, whether it's presentable in your court of law, whether it has any medical legal value, whether we have any responsibility for that those reports that being generated from the AI. And another thing is that there is a integration into the clinical workflow. That means that whatever the reports being generated, whatever the images being generated, it is to be also converted into your electronic health records, so that this can be used for the future perspective whenever the patient comes in future. So those records can be used, and there it will be also dependent on the high quality input data. So if there is a echocardiographic window is poor, and if the image quality is not at par, so the AI function also hampers. So even the report generated will not show that the image quality was bad or something like that. So it will not take responsibility for that thing.
Absolutely agree with you. And obviously, the AI will not explain. AI has given you reports, some results. It will not explain you.
Exactly.
Why?
If the reports are wrong, if you ask AI that why the reports is not corroborating with the actual patient thing, it will not give you back in something like that.
Thank you. Nicely explained. Dr. Sudodev, and how can you overall compare AI versus manual echocardiography? So far, we have discussed some good and bad things about AI and manual echocardiography. How do you compare?
Yeah, so by this time we have discussed about the advantages and pitfalls of both AI and the manual modes. So it's time to compare both modalities. So we can do the comparison based on a few points. So in the point of speed, AI obviously overscores over the manual mode, because the speed of the examination, the speed of analysis, and speed of giving outputs, all the results is obviously much lesser in the AI mode. So in that point, it is definitely better than the manual mode. The reproducibility, definitely AI is much better, because it is the machine driven, the machine done work. So the machine can do the same thing over and over again, and for the same data, and can give the same result again and again in comparison to a normal observer, which can be variable. But the point is, the crux is, in case of complex interpretation, for example, in complex pathologies, in complex congenital heart diseases, in complex adult pathologies, in those cases, there are subtle changes in the myocardium or subtle changes in the heart's condition that needs to be input, needs to be given to the machine, needs to be fed to the machine separately. So those things may not be well fed or may not be well given to the machine. And that's why the AI-driven results may not be that good or that accurate. And the most important thing is the clinical judgment. See, the anesthetist who is there at the head end, he can see the whole of the condition, the patient's condition, he can see the heart actually, he can see the monitors, he knows the overall condition, he can see the hemodynamics at that moment. So all these things, all these clinical parameters and all this judgment, that comes into play for making a diagnosis, a complete comprehensive diagnosis at that point of time. So in the interpretive period particularly, it's very important that a vigilant anesthetist who can see the overall condition and can put those data in the machine, that is the anesthetist manual mode along with the AI mode combined, gives the best results or the best outcome to the patient.
That's an excellent answer. Obviously, you will not treat a number given by the AI. It has to be interpreted by a human. Thank you. Dr. Arnav, is AI in echocardiography validated till?
So this is a very important thing. Firstly, I'll just highlight this article here. It was published in 2021, actually. So here, what they did was, the idea behind this article was to formulate a deep learning algorithm to assist novices. So what it was done is that eight nurses who did not have any prior echocardiography training were made to do echocardiography on 30 patients each with AI guidance. So it was then compared with scans done by experienced echocardiographers. So what the results showed, they were actually very good. So approximately 98.8% cases were diagnosed with good clarity for LV function and LV structure, LV size, and also non-trivial pericardial effusion, and also 92.5% cases RV size was also measured accurately. So this is actually helpful in scenarios where sir said that where the echocardiographer has a huge load of patients. So someone who is a novice but is under a controlled environment, he or she can perform echocardiography and just evaluate the patient at the first go. So it is very important. So is it validated? Further research is actually needed for this purpose, and but definitely it holds promise, and but in a controlled environment is needed for this purpose.
Absolutely agree with you and like your comment, controlled environment. That is what is very important. Anything may be validated, but until used properly can be erroneous. As an AI an example. Lini, any ethical concerns, commonly asked questions about AI, robotics, anything? Do you have any? Do you think?
Yes, there is a significant ethical concern while using AI. So the first is the bias and discrimination in AI algorithms. So as you have seen that AI works on a big data set. So this data set may or may not cover all the ethnicities, all the genders. So there can be a bias while measuring the values. Then number two, the potential for AI to replace the human jobs. I think this is a topic for debate for a long time. Yes, definitely anything quick, anything more efficient can always replace us. So we are at a risk. It can decrease the employment rates. The impact on clinician-patient relationship. If we are dependent totally on AI for making a decision about the surgery or conservative strategy about the treatment of patient, then the patient can or the patient party can feel unheard. The connection the patient party has or the patient has with the doctor can be affected. Then number four, data security and privacy. All the AI measurements, all the eco measurements that we are doing along with the AI, they all get stored for increasing the big data size on which the machine learning or deep learning is based on. So the privacy is hindered. And lastly, potential for over reliance on technology. Yeah, definitely the clinician may lose some skills that we had earlier. As we have seen in the last lecture by Satyajit sir, there was an image in which the clinician was lying on the sofa. Maybe it can be a risk.
Yeah, so at the long term, using too much of AI can cause depression. You may not think like you're an echocardiographer. You're just a machine operator, maybe not a clinician. Thank you very much for your answer. So, just an example how actually complete AI derived software gives the echo report, and as you suggested, as you discussed earlier, it can give any diagnosis like cardiomyopathy. Even they can say it's a restrictive cardiomyopathy, but even giving the diagnosis of amyloidosis. So it's a huge improvement. AI has gone far away, and actually this Ultramix it's approved by USA FDA. So above all, there are promises of the AI. Say someone is there in the extreme rural area, remote areas where there is no echocardiographer, no cardiologist. Even an AI tool can be used and give the number. At least if they know the ejection fraction is low, 20-30% something, at least some number is there. They know this is an urgent situation, patient has to be shifted. So in a remote area or unsupervised area, still it can be used as a primary guidance. That's what I think. And for the medical education, for simulators, AI can be great tool for the medical students. These are absolutely positive effects of the AI. And before concluding this session, I'll ask a question to all four panelists one by one. Abhinandan, can AI replace echocardiographers? Yes or no?
No, sir, never.
No. Or no?
No, sir, I don't think it can be done.
Suddhadev?
It cannot actually replace, but the combined effect is the best. Means the AI along with the echocardiographer. So both are required to make a complete diagnosis.
Okay. Lini, what do you think?
definitely it can't replace the echocardiographers.
Anyone from audience? Most of your answers? Yes or no? No.
AI can't replace, it always augments. And just to supplement Dr. Lini's second statement, so if there is any student, don't get disheartened. There is no job loss perspective in cardiac anesthesia as per se, because your credential may go down. There may be a probability that someone who did MD in anesthesiology or he's simply anesthesiology, cardiac surgeon may say ki, you don't need to be credentialed for a cardiac anesthesia. You come to the OT, I do have machine which is having AI, which is going to tell me everything about the cardiac parameter from your cardiac anesthesia perspective. So that is the only probability. So job loss, I don't think it will be there.
Okay, so I asked these questions to artificial intelligence. I asked it to chat GPT, and what chat GPT answered. So final thought, AI will augment, not replace echocardiographers, as you mentioned rightly. Just like calculators didn't replace mathematicians, AI will become a powerful tool for faster, more accurate, and accessible echocardiography, but the trained echocardiographer remains essential, answered by artificial intelligence. Thank you very much for today, and all the best.
That was an excellent presentation, very inspiring to all of us, especially the students who are having the decision to take cardiac anesthesia fellowships or DM in cardiac anesthesia. Thank you very much, Arubda and all the panelists for the excellent presentation. We'll be moving on our next lecture, that is the predictive analytics for the post-operative outcomes. That is AI tools for predicting the low cardiac output syndromes, AKI, ICU smart alarms for all the cardiac events. This is one of the most important topics in our cardiac anesthesia practice, that is the ICU practice. The speaker is Dr. Chandrashish Chakraborty. He is a senior consultant, critical care medicine in Mukundapur, Monipal Hospitals, Mukundapur at present. He is a fellow in critical care medicine from USA and having European diploma in respiratory medicine and the intensive care. Sir, please come and enlighten us on this very important topic.
Hello. First of all, I would like to thank Dr. Mona Lisa for inviting me to this talk. I'm probably the odd man out here because I'm not a cardiac anesthesiologist. I mostly work in the intensive care background. So when Mona Lisa gave me the topic to talk on AI in predictive perioperative outcomes after cardiothoracic surgery, it was a very surprising moment for me. But somehow I have managed to gather some information, and with the help of your expertise, I guess we can learn together about how AI is changing or is probably going to change the predictive and finally implementing treatment strategies in perioperative period. At the outset, I would like to apologize because I have a bad throat from being bit down the weather for some time. So for my squeaky voice, I just want to apologize. But if you cannot understand something, you can always stop me for my voice. But so the presentation basically will be taking you through the background and significance of why is it important to predict perioperative outcomes, what are the postoperative complications of interest, AI in predictive analytics, data collection and integration, AI models and algorithms, ICU smart alarms, challenges and ethical considerations, future directions and conclusion. So postoperative complications and statistics, the postoperative mortality is the third leading cause of global death. It amounts to around 4.2 million deaths per year. Just like it was very recently found out in a big study that human error is probably one of the commonest cause of deaths in the hospital. And the common complications that we find after cardiothoracic surgery are obviously low cardiac output syndromes, acute kidney injury, sepsis is always there. It's our bread and butter, especially of our intensivists. Cardiac surgery complications increase morbidity, mortality, hospital stay, and costs. Now, the significance of predictive analytics in cardiac surgery. Predicting adverse outcomes obviously reduces morbidity and sometimes mortality. Clinical decision making can be enhanced through early detection. And there are some traditional risk scoring like the STS or Euroscore, which only use static pre-operative data. So how does AI change this? Because this you can do even with the help of apps in your smartphones. Like I'll give you a simple example. You can calculate the GFR of a patient just from certain variables on your smartphone, and you have been doing it every day. Similarly, you can predict it for cardiac surgery. So how will AI change it, or how will AI add value? So AI will add value because it will not only take the preoperative records, it will not only take the preoperative records, EHR, or any wearable data. This wearable data is becoming very important nowadays. If you go to see a cardiologist and you say that I'm having palpitation, and if you wear an Apple phone or Apple Watch, then sometimes the cardiologist will keep your Apple Watch to scan the data. It is possible to scan the data and find out whether you are having arrhythmias at home. So wearable data, preoperative records, and electronic health records. So this is obviously there. Now coming to the intraoperative, which is the device data. How much vasopressors have been used, what has been the fluctuation of blood pressure, what has been the urine output, duration of anesthesia, what is your if you are doing a surgery on cardiopulmonary bypass, that what is the bypass time, etc. This is intraoperative data which AI will gather. Very important thing here is how much you are feeding to the AI. So if your machine is not connected or the data is not getting gathered, obviously you won't get a meaningful outcome. And post-operatively, again, you get the EHR data and the device data, which is continuous or intermittent. And taking the help of all this, it will predict complications and enhance clinical decision support. So what are the limitations of current risk prediction tools? Models don't incorporate intraoperative, postoperative, dynamic variables, and the patient status changes post-op affecting risks are not accounted for. So there's a need for a dynamic real-time predictive tools. Introducing AI and machine learning in healthcare. AI and machine learning enable pattern recognition in large data sets. We have already heard about it. So the first layer, which is, the machine learning, which just now we heard in the panel discussion, that it is just gathering data. It's just like lot of data being fed to it, and it just gathers the data. And then forecast risk by analyzing multiple complex variables. And this is where the AI models come in, like the XGBoost model, the forest models, etc., which is going to analyze complex data, which can be interrelated, which can be, or which can have different effect sizes on the outcome. For example, if you are having a diabetes, that will not have the same effect on the outcome, which let's say is kidney failure post-operatively, than a prolonged phase of hypotension during surgery. So the effect sizes are something that can also be forecast. Applications in ICU obviously include early warning. So you can be warned that even 12 hours earlier that this patient may go into AKI. Treatment recommendations, whether this patient who is currently having a low urine output, say 20 ml, 15 ml per hour, will this patient respond to fluids? Will this patient respond to diuretics? Or will this patient have a very high chance of moving on to dialysis? And then resource management. Artificial intelligence applications in perioperative period, early warning systems for sepsis, AKI, LCOS, predictive models, and improve patient risk stratification and proactive intervention. And this is very important because AI helps to risk stratify at a personal level or an individual level rather than that is what we are moving towards, that is a personalized or precision medicine or individualized medicine. We all know the meaning of low cardiac output after surgery, AKI, and both are common and serious potential problems. Predicting low cardiac output syndrome. So there are certain indicators like we know a low cardiac index, hypotension, vasopressor use, and the AI models analyze intraoperative and postoperative vital signs, and they can early detect and guide hemodynamic support and reduce complications. So this is a study which was retrospectively analyzed data from 1,681 patients who underwent cardiac surgery in a Chinese hospital from 2019 to 20. And low cardiac output was described as a cardiac index of less than 2.2, systolic blood pressure less than 90, certain signs of tissue hypoperfusion like raised lactate, etc., or the need for circulatory support, how much of vasoactive drugs you are requiring, whether you are only on norepinephrine, also with dobutamine, etc., and what is the dose. 6 patient learning algorithms were used to construct full and reduced low cardiac output syndrome prediction models. 13.4% were developing low cardiac output syndrome post-operatively. Now, if you look at this, this kind of this is called a SHAP summary plot. SHAP is one of the AI models which can interpret complex data. And this is the traditional bar plots. So there are various models which can integrate or analyze complex interacting data. These are like the random forest models, extreme gradient boosting models, that's the XGB. There are certain longitudinal AI models. That means they can predict at a time before the incident happens. And then we already heard in the panel discussion about deep learning and neural networks, which again have complex methods to predict outcome. And most of them are a non-invasive approach to predict low cardiac output syndrome, potentially reducing the need of certain invasive monitoring techniques. So if you look at the traditional bar plots, you can see, and this is basically the average impact on the model output magnitude on this side. So this is ejection fraction, then lactate, then diastolic diameters, mean blood pressure, etc., hypertension, etc., etc. And this is actually the SHAP algorithm. This is how it looks in the SHAP algorithm. And the length of this data actually tells you that what is the importance of a particular variable or how far a particular variable is influencing the outcome. For example, a high lactate will have a poor outcome, but a CVP or a creatinine or age will affect the outcome, but not to that extent. So that is the importance of these predictive models. It can give you, it can learn from the data that you're feeding and then refine the predictive analytics. A new machine learning algorithm to predict veno-arterial ECMO implantation after post-cardiotomy low cardiac output syndrome. So, post-cardiotomy low cardiac output syndrome occurs in around 2.4 to 13.5% of cardiac surgeries with bypass, and the mortality is almost 1 in 4. VECMO is a rescue for refractory cases or CPB weaning failure, we all know. But the optimal timing of implementing this is unclear. So early or OR implantation may actually improve outcomes. It's a retrospective study done in 2 Paris hospitals and with more than 6,000 cardiac surgeries. So it's a very robust data. 375 developed moderate to severe low cardiac output syndrome and 285 were included after exclusion. There are 50 perioperative variables on the basis of which this model was trained. And if you look at the algorithm area under the curve, it is very high. 0.86 is very accurate in predicting outcomes, predicting when a VECMO should be instituted. So there's a potential for early identification and proactive MCS initiation. This is a particular problem I find in my practice in ICU, and I'm sure in your practice in the OR and perioperative period, that because we don't work in, most of us don't work in socialized healthcare like say Paris or China or UK. So whenever there is a question of implementing procedures which are very costly, for example, putting on a VECMO or a VVECMO or an LVAD device or whatever, when it comes to the decision of one physician, that becomes a big responsibility for that physician to be very sure that this cost actually has a benefit, to convince the family, to convince the surgeon sometimes, and sometimes you don't have the time to gather more physicians to give opinion on that situation. So these predictive models can be a big help because this predictive model is unbiased. This predictive model does not know who is the patient, what is the paying capacity of that patient, etc. So these predictive models can be a very big unbiased help and support if once it says that this is the time where you should start thinking of putting them on ECMO. That becomes a big help for the physician to convince various family, etc., etc. Now, predicting AKI, this is more of a thing which we deal with, and there has been a lot of data and lot of publications on predicting AKI in critical care. In fact, there are apps being made and models being made, etc. So this is something that is not only in post-cardiothoracic surgery, but in critically ill patients anyway. So AKI prediction models use vital signs, labs, demographics, hemodynamics. And we all know that AKI is such a big problem in critical care and also in post-operative period that once you have an established AKI which is requiring dialysis, the chance that this patient is going to die even after a successful surgery goes up to 50%. So two patients, both had the same surgery, both had similarly good, outcome of the surgery per se, but goes into AKI and lands up in dialysis, has got 2:1 chance of dying. So that's a very, very high chance. Now, some of these prediction models could achieve an AUC of more than 0.884, predicting AKI within 14 hours of ICU admission. AI supports early preventive strategies like fluid management, nephrotoxic drug avoidance, etc. We all know this, but once the record is electronic, the AI can gather from the record that whether this patient was receiving or still receiving drugs which can worsen outcome, renal outcome. For example, a patient is getting ARBs and we forgot to stop it, etc., etc. Risk factors for CSA AKI include female sex, advanced age, low LV ejection fraction, comorbidities, pre-existing CKD, and intraoperative factors. So this is the incidence of AKI following cardiac procedures, and as you can see, the incidence varies depending upon what is the surgery. It is obviously higher in on-pump surgeries. It is higher with aortic valve surgeries, particularly open aortic valve surgeries, heart transplants, patients on LVAD, and the incidence of AKI on patients on ECMO is more than 60%, 44% of them requiring dialysis. So the risk predictors for AKI following cardiac procedures and surgery from multivariate analysis has shown you have got various preoperative factors like age, BMI, CKD, NYHA class, emergency surgery, and intraoperatively on-pump time, blood transfusion, cross-clamping time, use of IABPs, etc. Post-operatively, obviously, there are ventilation duration, infections, redo surgeries, low cardiac outputs. These are there. And there are some protective models. That's what is the baseline EGFR, patients on opium, etc. Now, coming to the HEART project. The HEART project is, it's a dynamic predictive analytics for cardiac surgery patients in CT ICU. It combines static pre-op and dynamic intraoperative and post-operative data. And it's focused on real-time risk scores for complication. And the model will predict adverse outcomes like AKI, atrial fibrillation, and prolonged ventilation using pre-op, intraop, and post-op data. So 200 static and dynamic variables per patient are collected. The sources I already mentioned before. The data warehouse is designed for secure integration and processing. The HEART project collects various physiological waveforms and clinical parameters from the electronic health records. So these waveforms, which is continuing, but we are probably not looking that minutely into these waveforms. We are looking probably just the mean blood pressure, but we are missing a diastolic blood pressure, which is say 45, can affect your kidney outcomes. The AI models consistently look at these data, not only intraoperatively, where obviously there's an anesthesiologist who is standing beside the patient, but postoperatively, where most of the time there is no physician at the bedside. The HEART project aims to predict 11 adverse outcomes, a broader focus than other models. The HEART project has real-time predictive capabilities. So how does it work? So if you look at the data collections, data sources, so monitor waveforms, vitals, EHR, OR cardiopulmonary bypass machine and monitors. Then this data is stored and processed in a HIPAA compliant data warehouse. We're talking about ethics in the previous panel discussion. So HIPAA is a very, its the full form is Health Insurance Portability and Accountability Act. HIPAA Act is very important, especially if you go and work in US. You have to get HIPAA trained so that the data of the patient does not go out, because all this data you are storing. So HIPAA compliant data warehouse and computation of patient risk, and finally it gives you a real-time feedback of adverse outcome prediction to care team. Data integration is a real-time streaming from monitors, data validation, cleaning, indexing, harmonizing different data types. What is data cleaning is there's a lot of noise in this data because because of various clerical factors, other factors that lines get dislodged, line gets kinked, lines are damped, etc. So all this data needs to be cleaned. Now, these are the machine learning algorithms used. I already mentioned this. These are complex algorithms like random forest, XGBoost, neural networks. And what they do is they not only look at just the data, but complex data which are interlinked. That means an ejection fraction and a baseline EGFR, this can be interlinked data. Because if somebody's ejection fraction before the surgery is poor, the EGFR will be low. So tensor decomposition for waveform analysis, explainability techniques like SHAP, I already showed a SHAP model. There are certain ensemble models. That means they can take the random forest, the XGBoost and neural networks together and give you a prediction where the AUC is even higher. The transition from conventional models such as logistic regression to machine learning models marks a significant improvement in recurrence risk predictions. And as you can see, these models, some of them can go with the area under the curve of more than 0.9. I think we have already talked about this. Model performance metrics are very high with AUC more than 0.75. Sensitivity and specificity ranges indicating model accuracy and positive predictive value improvements compared to clinician estimates. Finally, after LCOS, after AKI predicting shock, sepsis and shock, so Liu et al.'s model predicts septic shock before clinical deterioration. It identifies early warning time for interventions, and the concept applied in heart for various cardiac surgery complications. And these smart alarms, AI-powered alarms integrate multimodal data, as you all know, reduce alarm fatigue by improving specificity and sensitivity. Alarm fatigue is a very big problem, particularly for the nursing staff. And facilitate rapid response team preparedness. Example alarms for cardiac deterioration, alerts for hypotension, arrhythmia, low cardiac output events, delay in intervention correlated with worse outcomes, and AI alarms are triggered before clinical manifestations. Now, what are the challenges of clinical integration? So data standardization, obviously across device and formats, explainability to support clinician trust and adoption. Explainability means that it should be clear that how the AI is reaching a particular analysis or a particular prediction. There should be a clear understanding of how the AI thinks. Addressing false positive and alarm fatigues, and training clinical staff on AI tool use. We've already talked about ethical and regulatory considerations of having a trust over the AI, patient privacy, data security, transparency, and bias mitigation. Bias in AI is also a very big problem. The kind of data that you feed may be biased, as somebody was mentioning in the panel discussion, that most of these AI models are based on American patients, European models. So this is a huge bias because this is the data that has been fed to AI, and these bias mitigations becomes very important. What are the limitations and current gaps? They are mostly are validated retrospectively, limited prospective clinical trials demonstrating outcome improvements, variable data availability and quality. Despite high UC values, precision recall performance can be limited. For instance, models may generate 2 false alerts for every true alert, indicating room for improvement. You are measuring the true alerts and your AUC is high, but what about the false alerts? Machine learning algorithms are sometimes criticized as black boxes, meaning their decision-making process are not transparent, posing challenges in clinical interpretation and trust on the AI model. This is where explainability comes to picture. There are opportunities for improvement with multi-center data sharing, incorporation of more real-time data streams, and combining structured data with free existing image. Future is a seamless integration with EHR and monitoring system. This has not been done in our country till now. We don't have a seamless integration with the EHR of the OPD, OR, ICU, and the monitor from your cardiac anesthesia machine, ICU anesthesia, and ICU monitors, etc. As long as these integration doesn't happen, AI will not work. Development of intelligent clinical decision support systems and personalized medicine using AI for optimized patient care. We already summarized the key benefits. We have summarized the challenges of data heterogeneity and concluding AI predictive analytics and ICU smart alarms represent the future. Continuous model refinement necessary. AI will complement but does not replace clinical expertise. Thank you very much.
Thank you, Dr. Chandrashish. That was an excellent presentation. That this very important topic about the low cardiac output AKI and ICU smart alarms has been explained so well. Thank you, sir, for being with us. Thank you very much. So we will be moving on our next lecture, that is AI-based hemodynamic monitoring in cardiac surgery, the real-time prediction models, that is the hypotension prediction models, smart fluid responsiveness tools. So Mr. Chirag Maheshwari will be guiding us through this difficult topic. Thank you very much. Up to you, Mr. Chirag.
Thank you. Let me share my screen again on this topic.
Before starting,
can you see my screen?
Yeah, just 1 second. There is 2 questions on YouTube live chat box for Dr. Arup. There is 2 questions. One is from Dr. Muthu Kumar. What if the person does not take a correct image? If there is foreshortening of LV, how do AI recognize?
And so as you discussed, first and foremost thing for AI to work well accurately is to obtain a clear, good image. Now, if there is foreshortening and without any AI, what we do if we want to take say ejection fractions, it will be erroneous because the volume of the LV will be low. The AI nowadays still can recognize the view, say your 4-chamber view is foreshortened.
I'm sorry, is it directed towards me? I'm not sure.
Still AI will be able to recognize it's a four-chamber volume, but AI will assume that the volume of the LV is low. Accordingly, it will give the data, ejection fraction, volume, whatever. So it will be erroneous. That's why not all the data we should, leave on AI and take the results blindly. It has to be supervised and make sure the data is accurate. But with the latest machines like I'm using this Siemens SC2000 now, only you need LV long axis view. In that one view is accurate. From that view, it gives all the data. So now AI is becoming a more and more intelligent. Previously, it used to take 3-4 views for, say, stroke volume or strain. Now with the Siemens machine, I see just only one data set. It does everything: mitral valve analysis, aortic valve analysis, stroke volume, everything. So probably these biases, these problems will be overcome by the AI. So probably in future, AI will not just take one foreshortened view, but it will probably derive, it will be intelligent enough to know the other views are not foreshortened. I'll select the best view to give my result. Thank you.
Thank you very much. Excellent. There is another question from Dr. Molay Mondol. How many institutions in Kolkata are using AI-enabled TE right now?
Most of the institutes are using AI now. I think it's the whatever I know, the cardiac institutes, most of them use Philips machine. We personally use Philips CVX or Acuson AC2000, fully AI enabled. I think I'm the same for all the institutes. And particularly the transthoracic echoes, all departments have high-end machines.
Thank you very much. So we are proceeding up for our next presentation. Mr. Chirag Maheshwari, after you. Any other questions on this topic? Anyone? Okay, thank you.
Yeah, I can hear you. Okay,
Sir, the
I'll share my
stage is
screen
yours.
again.
Thank you, sir.
Yeah. So I'll quickly share some insights or thoughts on hypotension prediction index. So first of all, kind of just introduction and laying the setting the stage. So hemodynamic monitoring is crucial for patients in medical settings, operating rooms. It involves continuous assessment of cardiovascular parameters to understand like blood circulation. Generally, this has relied on invasive procedures which involve like pulmonary artery catheters. They provide accurate and direct and accurate measurements, but obviously, like as something being invasive, carries in risk like infections, bleeding, and other complications. Although non-invasive methods have been emerged, they have disadvantages, and AI kind of comes into picture by actually creating a system to get this information through these non-invasive techniques as well. Overall, there's in any way like even if you want to predict this, like there's a lot of challenges involved in doing so. Which are like just accurately predicting circulatory shock, determining optimal treatment because of existing diagnostic and prognostic techniques. And understanding the physiological mechanisms of this shock is actually very important for like actually guiding any kind of interventions. And in most cases, these management of hypertension like tends to be reactive and relies on like looking at the blood pressure trends and which can lead to delays in intervention. There has been some studies which show correlation between like mean arterial pressure, like short as name map, below 65 millimeter, and which like increase mortality in like non-cardiac patient populations, and which can also like apply to maybe our cardiac patients. So in there's such a case, like we can introduce this concept of like HPI or hypertension prediction index. It's an AI-driven system like developed by Hanti to predict hypertension. It uses a binary logistic regression model. Earlier we talked about a lot of like neural networks and all of those. So a logistic regression model is basically one layer of the neural network, and it's a simple kind of a simple prediction model where you take only specific features and then make a prediction on top of that. Like there is no abstraction, like there is no external abstraction involved. And it's known as an Acumen HPI algorithm, which basically is the implementation of this binary logistic regression for predicting hypertension. Through performance analysis, like what they've done is like taken a lot of different features and actually reduce it to a very small 23 predictions, so that it becomes a lot more simpler and like which can fit into a binary logistic regression model and make the prediction more interpretable as well. So what does Acumen HPI do? It basically is a parameter from 0 to 10. It gives you this parameter, but you can also set alerts on top of it, and also it provides a secondary screen, which also provides you any kind of information on why this prediction was given. So for example, like these are all you can see all the HPI parameters going into the model. And if HPI ever crosses your 85 threshold, it can give you a pop-up alert. And any physician or anesthesiologist can make an intervention based on that. And this is your secondary screen where it shows how you take kind of like given how the decision of an HPI like 94 was made, like what like map was involved. Maybe I'm not entirely sure like what all the different parameters are involved, but you make a decision tree based on that, which gives you this HPI. As we talked about, like what these like Acumen started with 2.6 million features, and which like turned into very specific 62 perform like analysis on like these 62 specific features, which led to finally reducing it to 23 predictive features. And these 23 predictive features, like some of the top ones were stroke volume, cardiac output, stroke volume variation, systemic vascular resistance, and cardiac contractility and dynamic elastance. So what the main objective of this HPI is to detect these any kind of fluctuations in these features and provide like a quick signal process all these signals and provide a quick number or kind of this metric to tell you that what is the probability or likelihood of hypertension occurring. How it was developed, it took data from 1,300 patients, or like more than 1,300 patients. You would do, as we talked about, like whenever you take data, you divide it into training and testing data set. There was divided into 293 training instances and 1,041 testing instances, and it uses cross validation. So cross validation is a more comprehensive way to test, which does that by actually training multiple modules and then testing on subsets of data and combining that information to actually give you a more comprehensive answer on like, hey, how this model is really doing. So it uses a very strong testing mechanism. From those from the analysis of like the using this HPI, like Acumen HPI, there was a study done on 702 patients, and which led to a lot of like reduced median time weighted average of MAP was observed, and it also reduced extended like hypertensive episodes because you could detect it earlier, and patient only spent like kind of a few minutes to with increased of MAP of 65 millimeter. So that's all from my end. I did wanted to go through another topic, which let me share my screen again for that.
Thank you, Mr. Maheshwari. We'll probably continue with another presentation of yours, Ethics and Human AI Interface in Anesthesia, the Medico-Legal Considerations.
Now I'm going to talk about human AI interface and ethics. So first of all, like just quickly going over the goals of this talk. First of all, talk about like explainable AI, what is interpretability or explainability, and how a model explain its decisions, usage, and then going from this, like what are the usage principles of AI? Like what are ethics we should involve? Like what are the legality concerns, and kind of like where the responsibility really lies when using AI. So it's important to kind of like ground this talk into an importance of like why this really matters. AI as like starts to do a lot more in your perioperative surgery spectrum. You want, like, it can flag vital signs, maybe predict certain risks on extreme end, also prescribe and recommend dosage of any kind of drug. For that, you need a lot of like ethical, legal, regulatory frameworks, which are still kind of like lagging right now. So education on this topic is really important. As you see from this comic, like, okay, like as a doctor, as a patient kind of comes to a doctor, like, hey, I'm hurting, but the doctor kind of just says, like, the computer says it's okay, like it has also given me a lot of reasons that you're okay. But if the patient is not looking, his head is still hurting, then there's something wrong. Like, it's something wrong in the prediction, something wrong in if the clinician is not able to predict or like interpret the model's like reasons correctly. So there can be many different failure modes in different parts of interpretability. But at the end of the day, any kind of decision taken in a hospital affect the safety of the patient. So we just don't want accurate AI. We also want explainable AI. So we want both explainable and accurate AI to actually make it function in a healthcare environment. I want to bring like focus out a little bit and talk about like what really interpretability and explainability are. First, explainability is actually a subset of interpretability. Interpretability, we want to understand the cause and effect of a model, like why it predicted the way, why it predicted something the way it did, and that should specifically be also be interpretable by the physician, and explainability is more on the model end. That, hey, like if given a model, can I understand why what part or feature it represents when I look at a specific variable or specific node in the neural network. So can it provide evidence that how certain things are how certain features are important to them. Explainability actually can be divided into multiple types of explainabilities. Some models which are much simpler are by design explainable or interpretable. But once you and most of the models we work on, which is gradient boosted trees or XGBs for short, any kind of neural network, or like even random forest, like these decision tree models also have like are become much more complex and are not really interpretable by design. For those cases, we need more post hoc interpretability, that once the model has been created, can we now interpret it. There are two types of post hoc interpretability. One, like model agnostic, that, are there certain methods which can work based on like be just model agnostic, that you can take any kind of model and actually do understand like what it means without really thinking about what kind of model you're using. And there are two, again, there are like there's subdivision like local and global. Local, I'll go over both of them in more detail, and then there's model specific, that, hey, like if there are certain techniques which only work for specific models, and we'll talk about them in the model specific section. First, by design, these are much more simpler models. So like just the model is simple. And what I mean by that is a model something like this, like a very simple decision rule or a tree, that a feature value is less than a certain threshold, then you go left. A feature value is above a certain threshold, you go right, and you do the same with another feature. So you can simply say that, hey, like because this value value A was smaller than this, and value B was smaller than this, that's why like the prediction was versical. So it's interpretable by design. Similarly, if you take a linear or a logistic regression model, which is a linear function, that means it can be represented as a multiplication of simple variables. So in those cases, you can say that if feature 1, your feature importance is basically beta 1. As x1 kind of changes, then the value of y will change based on how much how much beta 1 is, right? So these are also again interpretable by design, because these are simple, and you can just look into the model and say that this is what this is why the model made a decision given the features. But there are a lot more complicated methods, which I think we touched upon earlier in the last talk, which was sharp value. But these are basically are called like local model agnostic post hoc methods. Post hoc have we talked about, which means that these methods apply once the model has been trained, not before that, right? And model agnostic means you can work through any kind of model, so you can use the same technique on any kind of model. And local means it's giving you an information on interpretability of a specific type or a specific prediction. For example, if you look here, these are called individual conditional expectation curves, where here is like simple like predicted bike rentals. So what you're seeing here is for every instance or every data point in the data set, it's showing how if the temperature changes, how the bike rental is changing, the predicted bike rental is changing, and that is, and you can see that for each like temperature, humidity, and wind speed. So these are individual conditional expectation curves. There are more complex theories around this. One is the most commonly used is Shapley values or Sharp values. This is a technique which is grounded in game theory. Game theory is a concept in economics, but it's grounded. What it does is basically attributes the contribution of for a prediction to a certain feature. So it can tell us that, hey, like for this specific prediction, which features were important and how much they were for this specific for a specific prediction. And there are many more methods like LIME, which is I think based on like a locally surrogate model. In such a case, you train a more simpler model based once you've trained a complex model, you have your data input and your predictions. You can train a smaller or a very interpretable model, which is called a surrogate model, to do the same mapping from input to the output, and which becomes a more interpretable model, and use that as a surrogate or basically a proxy way to figure out how the bigger model or the complex model is predicting or making any kind of interpretations. For example, if you look at Sharp value here, this is showing based on the different feature values. If you have a feature value high, the Sharp value, basically the impact on model output, basically will reduce. So if the body mass G is very high, most of the time the predictions of the model are on the lower end, or it will end up reducing the final output value. And you can see that like if the body mass G is like on the lower end, then it's actually increasing the model output. So this is how you interpret a Sharp value graph. And then there are counterfactual explanations as well. This is how this method really works is you explain a prediction by actually giving it a counterfactual or an anti-example, and seeing how the model performs with an anti-example. So if I change a particular feature value to an extreme end, how the model is performing. So this also helps with kind of edge testing or stress testing a model. Then there's a global model agnostic post hoc methods. One is called kind of PDP, which is partial dependency plots. Permutation, like there are methods called permutation feature importance, leave one feature out, and surrogate models again, which we had earlier. But what global global interpretation is. It's more or like not for a specific prediction, but for a big data set, how the model is performing as a whole and not on a specific instance or a specific prediction. So this also gives you feature importance, which we call as like, hey, like this how important this feature has been in making the prediction. As you can see, like this is called like LOFO, which is the leave one feature out. In such a case, what you do is to understand the importance of the particular feature, you actually take that feature out and train a model without that feature. So now you understand and you see like how if the accuracy of the model has reduced, then the feature was really important. So this leave one feature out kind of helps you understand interpretability or explainability of the model based on training new models by removing a certain specific feature and checking how accuracy has dropped. If the accuracy has dropped, then this feature was really important. If the accuracy hasn't dropped, then feature was not that important. And this is something you can quantify with this technique. Now, coming to like these local and global interpretability techniques, we have this model-specific techniques, and this mostly applies to neural networks because neural networks are a lot more complex, and it's not easy to kind of like just like put a microscope on top of them and figure out what they're doing. So you have to develop very specific techniques to figure out what the model is doing or what the model is seeing. And some examples of model specific explainability is learned features, saliency maps, concepts, adversarial examples, again like counterfactuals, and influential examples, examples which might be very more influence and actually in the training data for making a prediction. I'll show an example of each of them. For example, we have these like, if you're training a classifier model, which can predict what you're seeing in an image, this is how something learned feature or learned features would look like. You would see in certain feature maps of the model, you'll see it's able to detect edges. In a certain layer of the model, it's able to detect textures. In a certain like another layer of the model, it's kind of goes even one step further or abstraction level further, where it's actually able to see blobs or circles, and then finally it's able to see actual images through even further abstraction of the features. Similarly, if you've seen these automated driving algorithms, they do the same thing. They basically create a real world map of what they're seeing in front of them, outside, and like around them through these lidar maps. But then they can also see like how they are actually interpreting each car and what path they are planning to follow across, to give you an explainable output of like what the model is seeing and how it's actually making its prediction. And here's another example for image detection, where, for example, here you have like a greyhound, Subal or Neil, and there are different techniques, smooth grad and grad cam, which you can see like how they actually highlight what they are looking at. So in this case, like this greyhound, this grad cam is actually showing that in case of greyhound, it's actually looking at the book, which is totally incorrect. So this helps you that to see that this model is not actually a good model, because when it's predicting greyhound, it's actually looking at the book and not the actual greyhound. Subol kind of works better, but then it's also kind of like looking at the whole image and isn't really giving us any kind of information of like which one is more important than the other for making the prediction. So there are more techniques that have evolved in this context, and they continue to evolve as this is an active area of research. But the model's landscape has kind of exploded in terms of like what kind of models there are. Like now there are LLMs which power utility of products like ChatGPT. So these LLMs are even harder to interpret or explain their reasons, although they are designed in a way that whenever you give a question and they need to give an answer, they always also have to give an explanation of the answer. But that's not enough. Like we need to look at inside how these models are doing, why these models are doing what they are doing, and can we actually have any kind of like cause and effect from these from the features they are seeing. These have there's like many challenges, obviously, because these have like billions of parameters. They have emergent behaviors which are like not explicitly programmed, and based on the question, they might actually take a totally different route on the in the neural network. So neural network, if you see it as a graph, it has so many different paths around, and LLMs can take a different path based on the weights, based on what the context was given as your prompt, and in a lot of cases, outputs can be confident but incorrect. So that's why it's very important to have like good explainability tools in place, such that you can see what the model is doing, and if the model, whatever the model is predicting, it's predicted correctly, but it's the reasoning behind its prediction is also correct, so that you can make sure that the model is sustainable and accurate. Here I have two examples here. For example, if you're looking at how an attention map of a model kind of looks like, that this eye is like mostly attending to the specific word, and it's attending to other specific words, and how they are so this attention map can help you see what the model is looking at. And Anthropic, one of the biggest LLM kind of players, are one of the also the top players in actually making LLMs explainable. So they did a research on looking at a specific layer of the model and looking at those like specific features on what actually makes them tick. Like if I use any kind of legal language or DNA sequence, like which neurons get activated more, and if you make them, if you actually uh, uh, intervene and actually change the value of these neurons, can I also change the value of can I also change the output and actually direct them towards the specific outputs? So this is a study they did. So every neuron might have certain concept actually encoded in those neurons, and we can kind of go and look just by these techniques to make sure like how the model gets affected given a certain feature value or a certain prediction. Then looking at model, and like there's so many different kind of models, right? Like available, like Claude, ChatGPT, there's Gemini, and for medical purposes, there is MedPalm by Google, and there's which you can use for kind of for obviously for medical purposes. But how do you really see which one is performing the best? So if you go on the internet, kind of like look for model card and leaderboard. This is a very important aspect of like whenever these companies release models, they also try to release a model card, which basically tells you about the limitations of the model, how it's performing on a certain data set. So for example, there's a leaderboard by Stanford called MedHelp, and it actually consists of multiple data sets. And what they do is whenever a new model comes out, specific LLMs, they evaluate it for accuracy and make sure they are like how they are doing in terms of like on each specific data set. So you can see if a model is actually good for that specific purpose or not. So just to remember, like no model is actually perfect in all cases. and benchmarking them is really important, and actually looking at these leaderboards and these model cards and making sure they are accurate is very important. At the same time, having like understanding these explainable techniques is really important to see and understand how model is actually explaining your output. Explainability, as you can see, like it's a very complicated concept, because you're giving these models zeros and ones, and it's giving you outputs in zeros and ones, but you want to interpret it in a way that it's understandable to the human, which makes it hard, right? And as we saw, these simpler models are much more explainable, easier to interpret, but complex models are like maybe more accurate, but they are harder to explain or interpretable. So there is a clear trade-off between accuracy and explainability. At the same time, because these models are actually making these multivariate predictions, as soon as you try to oversimplify it into one variable, even for the purpose of interpretability, you're basically misleading the interpretation itself, because you're with oversimplification. And in general, which method to use for interpretability, there is not much standardization, and there's not a lot of evaluation metrics involved with like how these explainability tools itself are doing. And at the same time, like on the other end of like oversimplification, there's overwhelming. So let's say we saw in hypotension prediction index, where it was giving you a decision tree of why it gave a HPI of 95. It showed many different variables, but if you're looking at too many different variables, it becomes harder for a clinician to or basically get overwhelmed with a complex explanation. So these are all the challenges with explainability, but it's still a very crucial and important concept to turn your head around and make it part of evaluating any kind of AI technique you put in your clinical workflow. There is obviously once you start to like take this model and actually put it into a real clinical setting, it has a lot of legal. It needs to take into like some legal considerations as well. As of now, I try to do a lot of research on this topic, but there's not a lot of progress has been made in the industry around this. Like as I understood, like responsibility and AI supported decision is basically pretty much murky. Like there's no clear answer on if the responsibility lies on the AI developer, on the AI itself, or kind of like the AI company, or the hospital who bought that system, or the hospital who created that system, or the doctor who's actually using that system. And I think that ties into that a lot more conversations need to happen to understand where responsibility lies, and how we can create the frameworks and regulation to make sure these systems are used in a way that does not harm the patient at the end. And as of now, as I understand, like there's the ultimate responsibility of patient care is on the physician, which is a hard truth, and it's on physician to make sure the AI they are using or the system they are using are up to par, are accurate, explainable, and they also understand how it really works, and kind of like whenever the time comes when it's making wrong decisions, or it's able to override its decisions as needed. And in human AI interaction, you need this, you need to make sure that human is always in the loop. Like it can provide kind of some kind of decision support and automation, but there should always be a clinician override built in. You should always be able to say that, yeah, no, I think there's something wrong. and reject the output of the model and go and do the right thing. So the interfaces, these AI systems should always should try to inform the clinician based on explainable outputs and not obscure these outputs in terms and make it more complex for the physician. And at the end of the day, the physician also needs to learn how to use these techniques in a meaningful way, such that they don't create harm, and they also use it to its full potential. There are certain, as we've talked about so many things, obviously there are certain ethics we need to take into account when building such systems. Fairness is a very important one. Whenever you collect data for actually creating such a model or training any kind of new AI model, it needs to collect data from like all the diverse sources as possible, like from the different subgroups, from different and make sure any gaps in the subgroups are filled as newer versions of these systems or like as these systems evolve. Transparency and explainability is important, as we've talked about. Then privacy and data protection. These as these models ingest a lot of private data, healthcare data is like highly private to the patient. They should make sure there are proper privacy and security measures implemented in place to make sure the data doesn't leave the system. And the model can actually make a prediction based on just like any kind of non-personally identifiable information. Then there needs to be clear accountability and an understanding of ethical implications of these systems, how to use them, when oversight is required, when oversight is not required, and how to make sure these systems, not just the system, like the physician, the system, the AI vendor, and kind of hospital is making sure that the way this AI being implemented at the hospital or at anywhere in a clinical setting is following all the proper rules. And at the end, AI system is only for the common good to benefit humanity. And this is what we need to keep into account whenever we're building such systems. They should augment human capabilities and help us understand, not just like help us predict things, but also help us understand certain things better. For example, we have this model called AlphaGo sometime back, which was like basically designed to play the game Go. And in one case, it made a specific move, and that move has actually led to improvements in the game of Go itself. And it has and that's something what we want to learn from the model as well, that once you have created such a model, you can actually inspect it to understand how certain things function, and basically giving human more agency in understanding a particular how a particular thing functions. And then these models, these systems should be reliable and robust. They should not fall into issues when like any hardware fails, or if there are any software issues, or if there is an internet connection issue. And they should have good practices and kind of all the small security things involved to make sure these systems are like highly robust. Then they should apply these models are also applicable to laws and regulations, and any development of these models should comply with the same. So with this, I'll come to the end of my presentation. Thank you, everyone.
Thank you, sir.
to continue with into our next session, question and answer session with clarification of the medical legal issues. We have with us Mr. Chirag Maheshwari to continue, and Dr. Rahul Guho Vishwas, who is Senior Consultant Cardiac Anesthesia at NH, Kolkata.
Hi, hello, can you hear me?
Yes, sir.
Yes.
Yes, sir, you're audible.
Hi, Chirag, nice to have you in the meeting. And
Thank you for inviting me.
of course, a big thanks to the organizers for conducting a CME on a topic which I think is the need of the hour. And thanks for inviting me. I want to request the organizers if you can just share the few slides that I had sent, which I will use as pointers to have a discussion with Chirag. Or if you want me to share, that is also okay. Just let me know. Yeah.
So we are sharing the screen with you, sir.
No problem.
The full screen.
Yeah, you can go to the full screen mode.
Yes,
and may I request you to just turn to the next slide when
Yes,
it is needed.
Yes, sir.
Yeah, wonderful then.
Thank you, sir.
So it's great to be in the presence of a machine learning researcher and a computer scientist. And I was listening to Chirag's extremely detailed discussion on how these models are created. I remember that the decision tree for doctors when they pursue a career in medicine does not include mathematics. So, a lot of it is something which we have to put our head around and think about it. A few disclaimers before we start this short session. I am not a medical legal expert. I have no formal education in medical legal jurisprudence, other than the experience and the instinct of a clinician who has been working for years in cardiac anesthesia. That is all I have regarding avoiding patient harm. And the second disclaimer is that I am not an expert in this forum. I represent the thousands of doctors who are getting to understand that there is a new technological revolution which is making rapid strides in the field of medicine. Through media, through journals, a few journal articles here and there, many of them have not even got hold of an AI-enabled tool in their daily clinical practice. So I represent those doctors, and as I read about AI in medicine, there are a few questions that automatically come to my mind as a practicing clinician. And Chirag, I didn't take your permission before taking your name, if that's all right, I guess.
Definitely.
Yeah, thank you so much. You can call me Rahul. And so let's proceed with these disclaimers on a few questions on which I would want your learned opinion. Please proceed to the next slide. Yeah. So you have taken pains to explain the conflict between explainability and accuracy. For example, I'm a cardiac anesthesiologist. I am using an AI-enabled echocardiography machine, and I get the picture, an image of a 4-chamber heart with the 2 atria and the 2 ventricles. All I am supposed to do is outline the inner margin of the chambers, and then the AI takes over and gives me a whole lot of information about what is the contractile function of the heart, how relaxed the heart is, to the extent that is going inside and finding out hidden patterns, like whether this heart can actually go into a failure very soon, and the patient might need to be admitted in the hospital for heart failure. Now, all I am doing is basically just outlining the inner side of the chambers, and it's coming out with so much of information. You have talked about it. It's called the black box. Now, the problem to the clinician is, and I want you to share your insights into this, how much do I need to understand? How much can the AI programmer explain it to me? That's the second biggest thing. And more importantly, these two you have dealt in your presentation. What about the medical boards of the country and the health ministry, the government, regarding this use of AI-enabled tools in the hospital? Over to you, Chirag.
No, thank you. Thank you for your questions. I'll try to answer it like in different pieces, kind of take into account, first of all, as I said, like these methods are entirely black box, and definitely there needs to be a lot of work that goes into explainability, and at the same time, like explainability is not a silver bullet. It doesn't solve all issues, because as we saw it can be oversimplified or overcomplicated. So in general, to actually look at is the only way to actually fix this or is validate these systems in like real world scenarios. Once you use them, once you start to get acquainted with them, they should not be the decision maker at any point of time. Like they should be just your support. They give you information. They tell you that, hey, like this is what we think based on the information we have, and you still have to kind of like question it and decide it. It's like taking opinion from 10 people and like making a decision yourself. And about like how these medical boards and courts of law, I think overall they do need to step in, make the important regulatory framework, make sure all of these like medical boards, courts of law are kind of talking to each other, making sure that there is algorithm transparency. For example, we looked at that leaderboard, right? And that's a very important aspect, that hey, like we have collected this data for these specific groups of patients, and this is how this model is performing. So that accuracy needs to be taken into account if it's not 100% accurate. So the clinician should always kind of like trust the model, but also verify its result in a way that is possible. And it needs to go into part like training of any kind of device or any kind of software being created, at the same time that like how this is how you use, like this is we've seen the limitations of the model, this is where it fails, so keep a lookout for them. And overall, like the feedback loop needs to continue, because these tools are also at the same time are super beneficial as well. Like they are black box. I mean, humans are black box itself, right? Like if you tell me, like if you ask me, like why did you do something, there might be certain various reasons, but that are those reasons sensible to you or not, that can differ. So a lot of guidelines on how to use a certain device or a certain software which is AI enabled is also at the same time important. And the only way to actually to tackle data bias is to collect more data, is kind of collect more diverse kind of data sets, make sure your model performance is good on the different subgroups and not just on a specific subgroup. Like it needs to perform well on many different subgroups or different stratas of the data. And whoever the AI vendor is, whoever is creating the company is kind of like selling this device, they need to also be transparent about the limitation. It's like that nutrition label we have on our food. The same thing needs to happen for models. Like they needs to have a nutrition label that this is where they can fail, this is where they perform well, and this is how you should use them, or this is how you should be able to use them in your clinical workflow. So definitely a very important, like medical boards and courts of law like need to be really involved in the development, and like which techniques they allow to be used in clinical setting, and which techniques they make sure that the practices involved in the development of the AI are also up to par in terms of making sure that they are collecting data properly. They are removing PII data so that it's secure, and doing all kinds of stuff to make sure this the practice of AI development is safe and allows for proper testing, so that you can actually define what those limits are. If you don't stress test something, you can't know what the limitations are. So the stress testing of these devices is also important, and should be part of any kind of testing framework for these models.
Thank you so much. Yes, you said one vital thing, that they need to be, this AI-enabled tools need to be tried out in real-world clinical settings. And more importantly, the flaws that we find in those diagnoses need to be shared across the medical community. That there are certain serious flaws. For example, in this echocardiography, AI-enabled echocardiography machine. The FDA in the US is doing, I think, exceptional work in trying to certify these AI-enabled machines. And I think the drugs and the device regulatory bodies of every country need to go through a rigorous protocol of evaluating these machines. For example, that would be CDSCO in India, which has to rigorously go through all the research, test the machine, use experts, and then certify this machine so that some of the blame from the clinician can be shared with the regulatory authorities. That is one thing that can be done. The other thing that I noticed in your talk was that you said the final patient harm, the reason for patient harm has to be assigned to the clinician. The clinician will have to take the blame in case of an AI machine related wrong diagnosis. Can you tell us from which sources you came to this conclusion that the clinician is something like this coming out in the US? This kind of a verdict?
No, I think there's no verdict. I said it's more of a murky thing right now. I think there's no clear guidance on it. There's still kind of understanding why I say at least right now, why I think is the responsibility falls on the clinician. It's like I come from a framework of, let's not take an AI enabled device. Let's say like a stethoscope, a very simple device. And whenever like stethoscope is kind of like giving you helping you hear the beats of the heart. The same time, if there is something wrong with the stethoscope, the doctor, because they have used it so long, they know when the stethoscope is actually not performing correctly. So they know when they are failing, and because they have this AI fluency, or like basically they have this fluency of using this stethoscope. And if anything happens because the doctor didn't figure out that, hey, like this stethoscope was not working correctly, then that like legal responsibility, or that responsibility falls on the clinician. Same thing I think is with these like new kind of tools. Definitely they are more powerful, so it's harder to figure out when they are wrong. So that's why like this training and kind of continuous usage will help actually figuring out when they are failing, like when they are not giving the right prediction, or there's some murky or kind of janky parts are going on. So that's one of the reasons I kind of pointed out that the legal responsibility falls on the clinician. But it's a very murky place that there is no clear guideline on it, like regulatory bodies, like legal proceeding. Like there have not been a lot of cases as well where okay, the misdiagnosis has been attributed to AI, like right now, because it's also not have gotten like integrated so much in clinical workflows yet. And we'll start to see some of these issues come maybe more often like later on, and which will require the need of building such legal framework, or where the responsibility lies. But I just feel like it isn't currently available right now. And when I say like where the legal responsibility falls on, that's more of out of analogy.
run-of-the-mill chest X-ray, a very simple imaging that you do almost in thousands every day in several hospitals. Those are getting automated by AI-enabled readers, which have been fed through millions of chest X-ray images, and they will tell us this guy has pneumonia or this guy has a pneumothorax. Now, the worry is being the behavior of the human is that if you give him a tool which is extremely helpful, that person will start to relax. Because in medical school, so far, the student has to go through tons of books to understand a simple electrocardiogram or the 8 or 10 different things to look in a very routine chest X-ray. That is study time, understanding, and now you have a machine which just tells you that this patient has a heart attack or this patient has a pneumonia. So this is something which I read is called a automation bias, leading to de-skilling and over faith of the clinician in the machine. Now, compared to India, the United States must be having many more AI-enabled tools at the moment in some of the big hospitals. My concern is with the patient that I come with a chest pain and come to the emergency of a very big hospital, and I don't know that they are using some AI-enabled ECG machine, which has been fed through millions of MI data. And it just comes out with that this patient has an acute heart attack. So as a patient, do you think that these hospitals need to come out with some kind of a disclaimer or a notification that please understand we are an AI-enabled healthcare service and certain decisions are being taken through AI? What is your opinion?
I think AI decision making needs to come through consent for sure. There's no doubt. Like if like and this problem is not just like in healthcare. It's kind of like, let's say, insurance, like kind of claims, or like even in many places this is definitely an issue, and like a lot more decisions are taken about you based on these algorithms, and it's so yes, I think like the patient should be like told, at least like sign a form or like be given this disclaimer that your whatever like triaging we are doing, kind of like like looking at the X-rays or like radiology, is being done through an AI-enabled device, and they should have the right to like get a second opinion from a different from a different place or without AI as well. And as you so there's no doubt. I think there definitely needs to be a system in place where I should be able to go back and ask that can you give me a more human interpretation of this. I think like the decision has come out to be wrong. I'm still feeling pain, and why my why my prediction or my came out as like no, I have no issues. So this that there should be some frameworks for that. As I do see like the larger hospitals, that can be a complication, because now you're working with something like much more opaque, even not just like from an AI perspective, but from like in a hospital or doctor perspective, that you might not be directly interacting with any kind of radiologist. So you need to be need to be told like why how this decision was made, and if there has been and these tools also need to be explainable, right? Like if it's saying that there's no pneumonia, is it showing that is it showing that there is no places in pneumonia, or what are kind of even like any counterfactuals available there? So you need to like put these systems in place, not just with that, hey, like just give me a prediction, but also like an explanation which helps with making sure the prediction is correct. But at the very end, I think that this is definitely an issue, and I think not a lot of people or not a lot of systems have kind of like figured out what the right way is. or right path is. But as the technology is evolving, and like we should learn how to incorporate this. It's like we have Google Maps, or like as kind of phones came along, we stopped remembering anyone's phone numbers. It now is just like and that over reliance or like de-skilling comes in various forms. And like me as a programmer, these AI tools are actually being targeted towards co-programming as well. So it always constitutes that, hey, like this is something, should like, am I de-skilling, or am I kind of not learning programming enough? Like, well, and I think this is definitely a problem for newcomers into the industry. And this is same with doctors. Like if a doctor has already like seen an AI tool across his career, then yes, they might not be able to do anything without it. And I think in one way that is wrong, but if you look at the other way, if this AI tool becomes pervasive enough, then that's okay, right? Like before MRI machines were invented, no one could actually kind of like see behind. But once MRI machines kind of came along, you could see a lot further. But you don't fully rely on it, but you do believe, like, okay, that when it's available, you can use it in the right way. And same with AI tools, you have to figure out, like as a clinician, figure out what makes sense. How do I not reduce my skills and like overly rely on it? And that again, like, needs to be part of like curriculum in making sure that clinicians are judged on kind of not just like are they able to use the tool, but are they able to use the tool correctly, and interpret its results, and also make the right right like give the right care based on that interpretation or decision. So I think these are very murky, like very hard questions, in the sense that no one has the right answer here, and everyone is kind of like figuring out as the technology is evolving, like how do we do this, like how it's but I think certain principles like do need to be taken into account, that we need, even when the autopilot is on, we need to have the control. Like even when the autopilot, I should have the steering wheel and kind of like make sure take the control on time. These are, and like not erode my core skills, that I am able to, like, for example, as a programmer, I'm able to make good software systems, which if like which some part of the code might have been written by AI, but most of the design and everything has been done by me. So that making sure I have core skills, and some of the like the smaller, easier work is offloaded to these AI systems.
Fantastic, fantastic. I completely agree. I mean, technology has to be integrated in daily practice. There's no question of that. We can't go back to the age of lanterns. We need to figure out how to be still safe when using these advanced systems. And one thing came out from this discussion is that probably for the time being, some kind of an informed consent from the patient should be taken, that this hospital uses advanced AI systems. And although there's a clinician behind it, you need to know that these systems are pretty much in place. And you can ask me questions on how they are being used and all that. Yeah, fantastic.
And I think some of the cases, like just to add a like little bit more information to that, like even when giving to the patient, like giving a prediction to the patient, it might be good to kind of, as it directly involves the patient, that how the explainability tool is also part of it, right? Like when you're that this is what the AI model saw. This is how the AI models are also explaining your condition. So in that case, patient can actually like question it more easily, and kind of come back and make sure that they get a second opinion.
Fantastic, fantastic. Can we go to the next slide, please? Yeah, so this is very much up your lane. are vulnerable to bias. For example, and I'll give you an example, when we do clinical research, we tend to leave out the vulnerable population from that clinical research. For example, small children, pregnant women, very elderly people, they are most often, in most of the clinical research, those patient subsets are not included because they might have a more adverse effect from the experiment. Now, for that reason only, medical literature itself is biased. And often clinical research will be done on socioeconomically poor backgrounds, as we have historically seen that the tribes and, for example, the Black population might be more exposed to some of the more cutting edge research and all those. So that is one part of the problem, because the AI systems are being fed this medical literature to try and have an understanding of what might happen to the patient. So first of all, there is an inbuilt bias, which is again going into system. And then the other thing that I understand is that there might be a possibility that the clinician is using this particular AI tool completely out of context. It was not meant for this particular indication, but what we call as off-level, that kind of an indication is being used for a AI system. And then there are the things like you know best as software problems or hardware flaws. Now, being a developer, an AI programmer in medicine, can you tell me in 4 or 5 points that how are you taking care that least patient harm happens from introducing AI to medicine?
Thank you for this question. I think, and so yeah, this is a very interesting question. First of all, as FDA classifies software as a medical device, even like any kind of AI tool also comes into this same framework. But obviously, software previously was a lot more predictable. That every time you give X, you always get the same Y. Like you give the same X, you get the same Y. But in AI systems, if you give an X, like a different Y might come out, and that's kind of a fallibility of these models, but also actually are a benefit of these models, like which like in LLM's cases, that it helps them be more creative, because you can get these different or random outputs for the same input. But in case of medical scenarios, you want this reproducibility. Like again, you want the same X to always give the same Y, and that's a very important thing we want to make sure in ML models we create, so that there's the reproducibility is very important, and not just like reproducibility of but like reproducibility of all the experiments we do of all, and which makes sure that anything that goes wrong is well documented, or anything that's going right is also well documented. So like we kind of just follow like certain principles or certain approaches, which is rigorous validation is really important, and like robustness or reliability is baked into different layers of the system. Like for sure, there can be hardware failures, there can be software failures, but hardware on its own is kind of should be reliable on its own. For example, like if a machine goes down, like another machine should come up on time to make sure like these hardware failures don't affect like the overall system. And like you see Google never going down, but google.com never going down, but they have at any instance in time, they have thousands of servers actually failing and new thousands of servers coming online. So they have these like systems to make sure these overall, when you look from a zoom out surface, they seem very reliable and robust, but they are failing internally. And it's just that the system, or kind of the complex system you've created on top of it, make sure that any of these harms don't affect the end users. And the same thing like needs to happen, should we try to bake it into like AI validation or AI like reliability, that these are like validated, these models are stress testers, and once a model actually goes into the market, there needs to be post-model like post-market monitoring as well. Like, are these models doing well? Are they like and the clinician should be able to give feedback like, hey, like I saw that this didn't go well, and they should be able they should easily be able to kind of give a feedback in that case, and there should be a clear audit trail of those feedback. And you talked about kind of going off label. I think that's like a weird scenario. Is like, okay, like you've designed a system to work in certain scenarios, and if you're like using it outside of that certain like that controlled environment, then now it can fail. I think that's something from an AI developer perspective. I think that's hard to control, because you can't really you can create guidelines. You can make sure like this is at least you can as a AI developer you can make sure what that label is. But if somebody goes out of that label and kind of use it in a different setting, that's somewhat what the AI developer can't do. But that is what I think we need to talk about, like that AI fluency, that in figuring out that this is where this technique works, and this is where only I should be able to use it. And at any system, to make it reliable, there's only one basic way. Like you can't have any single point of failures. And so to make an AI system kind of like reliable and like not have any system failure, you have to bake that into the workflow, that any kind of prediction that is coming out is also being verified with like explainability, is also being verified by the clinician. So because it's not being used as kind of like the decision maker, but a decision supporter. And just to like, if you have all these practices in place, that does make it reliable, not 100%, but I think it puts it into the right direction.
Wonderful, wonderful. And I have no doubt that the cutting edge AI programmers are stringently validating their system, test, and wherever there is a problem, wherever there is a flaw, they are working on it. But the most important thing which you told was what we call a phase 4 trial. When the product comes out in the market, you extensively take it out after commercialization. Let the clinicians play with those things, find out with their sound clinical judgment where it is going off track, and use research as a clinical tool to share their concerns with the global clinician community. That, for example, this particular AI-layered echocardiography machine has these certain flaws. Not only will it help the patient, but it will also help the programmer, the developer to absolutely go ahead
and improve
sort
those.
out
Yeah,
those flaws.
exactly.
Yeah, absolutely.
I think
Absolutely.
it's to develop this technology. Like, I mean, like when I was working in kind of pathology, I used to work kind of side by side with pathologists all the time, and that's the only way we could develop these models. There's no, I am not a domain expert in pathology. They are. So it's the development of these technologies also needs to go hand in hand with the doctor. And with the doctor and kind of like whatever you're working on, because at the end of the day, if you have to integrate these systems into their workflows, they should understand what's going on. And
Yes.
and they should be able to see like, oh, how this supports me and doesn't actually get in my way, instead and actually improve my workflow.
Fantastic. Meanwhile, the screen went black, which might be a subtle sign that the organizers are asking us to close.
Extremely sorry, sir.
Is
We
that
are
it,
running
Dr.
short
Mona
of
Lisa?
time.
Should we wrap this up?
Sir, can we just finish the discussion?
I think
with these slides
because
early, because we are running short of time.
Oh, okay. just quickly close this because we are way behind time, and I'm having great fun in talking to Chirag and understanding the wonderful work that he's doing. Yeah, so we have talked about it. So these systems are being learned by feeding a large amount of data from the electronic health records, the on-ground monitors that are being used to monitor the patients and all that. So that means that's a lot of private patient data which is going to develop this model. So Chirag, my question to you is, how is US handling the privacy aspect of patient data in developing clinical AI models? And that would be my last question. Thank you.
Yeah, thanks, Rahul. This is a very important question, and like a very crucial one, because I think this is not just like a AI related kind of an issue, but like software in general, like especially that handles any kind of healthcare data. So there are very specific techniques, and this is, I would say, in some sense, is a solved, like a lot more solved problem compared to other things we've talked about. When it's like privacy concerns can be taken care of by making sure like all the data being stored is encrypted, both both in transit and in rest. Like basically when it's stored and in any kind of hard drive or any kind of like basically on cloud storage, it's encrypted. That's very important. And even when it's moving through the network, basically internet, being transferred from one hospital to another, or kind of like from patient, like it needs to be encrypted in transit. So that helps to make sure at least like elevate a lot of privacy concerns. The second being, we call it like basically sanitization, or you could call it like anonymization. Basically, you need the vital signs, and you don't really need like the personally identifiable information to actually train the model. You don't need the name of the patient. You don't need the like maybe the race of the patient, right? Like or like you don't need all of this information to actually like develop certain models, and they can be anonymized or removed entirely, like whenever you're ingesting that data. So the AI vendors, whoever like developing these models, they need to make sure they have this pipeline of whenever they're ingesting these data, they first of all they are encrypted, and they are de-identifying any personally identifiable information before analysis. And you must have heard of GDPR, and there are a lot, like basically there are a lot of like laws around this, like data privacy as well, which provide certain guidelines that if my data is being used, I am entitled to get that data anytime I want. Like I am entitled to ask whoever is storing my data to say like, please delete it. I don't want like I don't want you holding on to my data. And any AI vendor or anyone who's actually ingesting this data needs to actually implement these GDPR techniques or GDPR laws into the system, so that the user can anytime access their data, or ask the vendor to delete that data, or there are certain time to live, which is basically which basically means that after a certain point of time, you would automatically delete my data. You wouldn't keep it for like forever. So just these techniques help to make sure that like privacy concerns are tackled. But at the same time, there are like from an ML perspective, there are also techniques which make sure like make sure of like privacy preservance, which is called federated learning. So for example, if I'm like learning, if I'm added um, if I'm trying to train a model from a particular user, you don't actually need the data itself. You actually need the gradients of the data. What that means is like I was talking about, like you pass a training instance through the network, you get the loss, and then you flow the gradients, and that updates the model. So updating the model only requires the gradients, and that is something that does not have any kind of actually patient identifiable information. So in some sense, ML can easily be privacy preserving.
Wonderful, cool. It's very reassuring to see that two things you said. One is there are enough regulatory checks and balances to see that personal patient information is not disclosed or harmed in any way. And the other thing that I came to know about is that AI developers also don't need those what we call table one data, the very personal information of a patient. They basically need certain features of that particular subset on which they work. So there is really a lot of concern which has been addressed by the current regulatory authorities and the AI vendors. So it was wonderful to talk to you, Chirag, and learned a lot of things regarding how these things are being made. And I take it over to the organizers, thanking them once again for conducting this session. Thank you.
Thank you very much, Dr. Rahul and Mr. Chira. Our sincere thanks to both of you for the excellent discussion and your depth of knowledge, the clarity, and the effort you both put to make this session a truly enriching and engaging for all of us. Thank you very much, sir. Thank you very much.
Thank you, Rahul. Thank you, Dr. Anesthesia.
We will move to our next session, that is AI the future of cardiac sciences? The promises, the pitfalls, and the future roadmap. It is my privilege to welcome Dr. Kunal Sarkar, one of the most distinguished names in cardiac surgery, a master of his craft, a visionary leader, and a compassionate healer. Dr. Sarkar has dedicated his life to saving hearts and inspiring minds. So with decades of surgical excellence and countless lives touched and the legacy of teaching and innovation, he stands as a true icon in our profession. So he stands as a true, we are indeed honored to have him with us today to share his wisdom and experience. Thank you, sir, for coming in this program. Thank you very much, sir.
I hope it's visible. Mona Lisa, Rituparna, all my friends and colleagues, personal gratitude. Thank you for giving me the opportunity. I was really becoming very, very worried because at this time of the afternoon, a combination of hypoglycemia and neuronal exhaustion is a very fatal combination. And I think you've at least taken care of one part of it. Thank you so much. The first use of AI in the medical community will be to make speakers stick to time, right? And I think this is a slide that was hanging outside an American Presbyterian church for many, many years. And this church, somewhere in the vicinity of Boston, said that artificial intelligence is no match for natural stupidity. And I think much of humanity probably still lives in this realm. এইটা সরবে
না না স্যার স্ক্রিনটা বড় আছে তো ঠিক আছে স্যার অসুবিধা হচ্ছে না
না আমি ঠিক আছে তোমার এখানে ঠিক আছে Yes. Now, quickly, you see, I'm obviously no granular expert in computation, but if you look at the fact that since 1939 or 1940, that what has been the whirlwind expansion in human computational ability, and I think this has really been a super exponential development. But still, a few pages of history remains of interest, because when we use the word algorithms, AI, all these things, we owe a large debt of credit to this 9th century mathematician from Damascus called Al-Khwarizmi. And Al-Khwarizmi, who really camped outside the Silk Route caravans, because from the Silk Route caravans, they used to smuggle the documents outside of India, because algebra was developed by Al-Khwarizmi based on the fundamentals of what is called Indian or Hindu mathematics at this stage. And the word algorithm is actually a Latin mispronunciation of Al-Khwarizmi's name. But computation came into its force. It had to wait for almost 2000 years, when in a very unfashionable town and vicinity, little north of London, called Bletchley Park, this fellow called Alan Turing, he devised this code-breaking machine called Enigma. And it was with the help of the Enigma machine that the German codes that were incessantly coming out of Germany were decoded by the British war machinery. And if there were a couple of interesting reasons why Britain, very low on resources, a much smaller military machinery compared to the then Germany, was able to resist Germany, it is because of scientific innovations like the Enigma machine. And the Enigma in 1939 and 40 was the real application of complex machine-led decoding computational power that we know of. The internet was officially born on 1st of April 1983, and that is a very different history. And we have to wait all this while in the year 2024, when Hinton and Hopefield were given the Nobel Prize for Artificial Intelligence. And what were they given the Nobel Prize for? They were given the Nobel Prize for physics, and the single most unhappy people were the physicists, because the physicists still today believe that artificial intelligence is not physics, and a whole world of Nobel awardees from physics has protested that Hopefield and Hinton should not have been given the Nobel Prize for physics. So they are artificially intelligent, but naturally very unhappy. So there is a whole lot of unhappiness in the Nobel community right now. Where are we regarding the adoption of AI in society? When you adopt any technology in society, you go through this phases, which is called the Gartner hype cycle. And in the Gartner hype cycle, first of all, we are now like excited adolescents. We are like excited children who's just got a new toy in hand. And we are in the first peak inflated phase of expectation. We are very happy. We are very euphoric. And this euphoria will have a very rapid decay. And the rapid decay through criticisms, through realization of errors and mistake, will result in a trough of disillusionment. It is like a young boy and girl falling in love. So this will go through the romantic cycle, through a hype, through the crest, through the trough, and from the trough, we will have a plateau of productivity. So where are we with AI today? It is like the love at first sight syndrome. We are very excited. We can see no faults right now, but I'm sure we will live through these different phases. Now, in healthcare, I think all of us realize that there was a famous song by Sting. I think this was an 80s soft pop hit, when they said, every breath you take and every move you make. So like the Sting song, Every little action, every little movement in healthcare generates data. Every phone call, every inquiry, every IP, every OPD, every financial bill, every operation, every death certificate, every victory, every defeat is an incessant data generating process. And as we are playing through this data turbulence now, we have to familiarize ourselves with the raw data, the algorithms. Algorithms are like your driving instructions, which are governing how the data will be handled. From the ocean of data that is being produced in the AI models will come the agents. The agents are like the little domains that you and I want to work in this huge spectrum of the AI. And remember one thing, because in the next 10 minutes, this will come out repeatedly, that we understand mathematics, we understand statistics, but we do not understand patterns. So what AI is working on, like a over enthusiastic child, it is not so much depending on our conventional statistical models. Perhaps it is, but it is incessantly looking for pattern recognition, and pattern recognition is something that you and I know nothing about. There are ample examples of this. There is a whole lot of work going on. Millions and millions of ECG data is being put in clinical large language models. And in this large language models, there was a hype a few months earlier that rather than our ST elevation and ST depression and Q waves appearing, they are trying to come out, which is something very different that will make earlier detection of myocardial infarction possible. But the question was how? The question was, what was the clinico-pathological correlation? Because mere recognition of some blip or some pattern will not satisfy the scientific queries a clinician has. So the work is still going on, but this again is pattern generated. Currently, when you apply for a health insurance and the health insurance asks for your ECG, so if you look through what the insurance company is actually calculating from the ECG, they are trying to calculate not just whether your heart looks good, whether your heart rate is regular and the rest of it, but the ECG actually has a formula that is able to calculate your chronological age as opposed to your biological age as opposed to your chronological age. So we are becoming like real estate. You may have two buildings, one is very poorly maintained, 10 years old, and one is a better maintained building which is 20 years old. So people will prefer the better maintained 20-year-old building than the shabbier maintained 10-year-old building. So currently, our date of birth and chronological age will become less and less relevant, because these people, by looking at an ECG, is able to predict that what is the biological age as opposed to the chronological age. I am told that half of your blood electrolytes can now be predicted through the large language models. They can tell you what your sodium potassium is, once again through your pattern recognition in ECG. But then again, can you and I go back and revalidate it? Remains an interesting question. The enhanced ECG interpretation, there is a lot of stiff competition amongst the device bearer, the watches, the medical devices, the non-invasive technology which is going on there, because people are trying to detect more and more. There is some definite progress in trying to predict ejection fraction from ECG. But then again, I believe the correlation is not too bad. But looking at this ECG, if that clever fellow tells you that, look, your ejection fraction is 40%, you and I, that may be correct. But will we take that as gospel truth? What will be the counter validation of it? How has this fellow done it? It is once again that is why I keep on writing this term pattern, 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 because human wisdom, our medical training, our didactic training, our intellectual processing, our 5 years in medical college and the rest of it, nowhere in our training have we ever been trained to detect patterns. And that is what the science has shifted to now. So heart failure, the heart failure territory is moving into the very rapidly into the pattern recognition territory. The accuracy rates are not too bad at this point of time, but will it be clinically validated is $1 million question. Now, something that we agree with, maybe with a little bit of reluctance, quantitative angiography will get into the field like the rest of your diagnostics, like the rest of your imaging. A lot of coronary angiography and your intravascular imaging will obviously go into the AI territory. Why? Because there you are looking at numbers, there you are looking at architectural subsets. You are looking at what is the percentage narrowing, you are looking at how much your lumen is gone, you are looking at what is your flow reserve. So this is not pattern recognition, this is actually recognizing the data and generating a report from it. So without a doubt, within the next few years, there is something now which is in operation, which is called a neutron beam CT scan. So with a neutron beam CT scan as opposed to an electron beam CT scan, the ability of the CT to give us clearer picture and merge it with flow data is going to be a lot easier, and inevitably the reports that will come out from these anatomical plus functional CT scans will be AI guided. There is a little bit of work right now which is trying to validate that how good are they? Is it really matching the analog evaluation? Now the results are good. CT angio is something which will be really facing, this is literally promising. You see, to cut a long story short, what we look at now in cardiology, you look at artery, you try to look at the intraluminal part of it, is the artery narrowed or not, and then try to predict that whether you, me, somewhere else has a coronary artery disease, whether you will run into trouble in future. Currently, what the Oxford group of people are coming up with is much before a coronary artery gets affected intraluminally, it is the tissues around the coronary artery that shows inflammation first. So we should now be able to predict coronary artery disease. Is this a thing? So we should be able to detect coronary artery disease by what is happening in the pericoronary zone even before the disease has gone inside the lumen. Because pericoronary inflammation, people like us who are plumbing day in and day out with coronary arteries, we know that whenever you open a diseased coronary, inevitably the tissues around it are inflamed. So you will be able to pick it up much faster. Echocardiography has been discussed at length. The only trouble, make no mistake, if you want to hang on to your echocardiography and not lose it to a machine, don't lose the control of the probe. 3 machines are being developed now where the use of the probe will be automated. You are going to have 3 probes, just like a CT scan. You slide inside it. None of these wriggling around and changing positions. You are going to have prefixed images taken and the results will come out. If you are interested that which database currently holds the largest number of echo images, it is something called EcoNet Dynamic. So EcoNet Dynamic holds a large repository of echo data, And the only thing that is saving the echocardiographers from extinction is the fact that the probe is handheld. The very minute you lose control of the probe, you are history. No human being will be doing any more echocardiograms, you take it from me. Chest X-ray is already lost, ultrasound is on the way to extinction, so hang on to your echo probes. Now, echo is going through a lot of analysis. There are very large language models which are trying to look at structural heart anatomy, because it is obviously it's not all about calculating ejection fractions and the rest of it. A whole lot of complex work is happening in the echo domain. Interesting part is predicting heart failure. Predicting heart failure, if you have a series of echoes and ECG, can we really predict the clinical course that the heart failure patients will, how are they going to clinically behave in the near future, is a very interesting thing. And the Americans are doing good work on it, but they're losing interest because they now have more hearts than they need to transplant. So basically, they were doing a lot of work before when they had organ shortage. So now they have more hearts. You know, they are wasting more than 100 hearts a year. So they have more hearts than they have transplant waiting list. So the activity in this area has slowed down. The real interesting points, you know, when we have operated all these complex cases, heart failure, people who've stayed in ITU for more than a week, etc., their follow-up at home in the community, rather than just depending upon the love and care of mother or wife, will now be dependent by all these non-invasive sensors. And the interesting part of this is called ballistocardiography. When you measure an ECG, it is electrocardiography. And ECG picks up the electrical current. The ballistocardiography picks up the vibrations. So if you have enough sensors mapping your body and just lie on a sensor-positive mattress or a sensor-positive device, many of our hospitals have it. You may not be aware of it. We have these sensor blankets right now. Last year, when I was in hospital for 4 or 5 days, I actually lay on them. And every night you can get your pulse, blood pressure, and even the cleverer ones can give your SpO2 at this point of time. So this is something very good, and this will improve patient surveillance at home. In our cardiac domain, where I think a lot of the human interpretational bias or mistakes can be taken out is in complex areas like post-transplant allograft rejection. Now, post-transplant allograft rejection, especially through Ann Arbor and other units in US, they have almost become mechanized. We are doing fairly okay in our transplant activity now, and I'm trying to get our post-transplant biopsies sent into this database as well, because this will be of big use. As anesthetists, you are very interested in risk prediction. You should be. We should be doing a risk predictor calculator for calculation for whatever patients we take in. You know of the STS database, the Euroscore risk calculator, but this is now getting into the AI domain right now. They have incorporated at least 15, 20 more variables, and when you plug it into the AI agent, I believe a risk prediction comes out, which is kind of even more accurate. It's a complex process. I'm not getting into it. You see, a fundamental question, I was listening to our friends discussing later on, and as clinicians, we have to harp on this topic again, and again, which is, say, if AI is so clever, AI is clever without a doubt. The intellectual capacity, the computational capacity of AI is many times more than what you and I have. But AI's methods is not something you and I understand. For example, if you had the 5,000 patients data, say from Syntax trial, so without doing the statistics yourself, would you really fit it into a large language model and ask the large language model that tell us how did angioplasty and CABG fare after 5 years? Because it will give you, I don't think anybody has done it so far. If you have the data of the 5,000 patients with you, instead of going through the Kaplan-Myers and your statistical significance, the 4 or 5 statistical tools the you and I are aware of, if you fed it into a large language model, you may get a different conclusion altogether. Because AI is only partially conventional knowledge. The rest of AI is pattern recognition, which we know nothing about. People are talking about clinical trials in the AI domain. The whole trouble is you are going to have a lot of fancy mathematics from it, but there is no way you will be able to validate it because our conventional teaching knowledge does not include pattern recognition. But there is some real interesting use. And this use is something that fascinates me. And I hope in cardiac surgery we will get into it sooner rather than later. This is a hepatic resection going on. And with the hepatic resection, they are doing it robotically. So they have the robotic hepatic resection, they have the CT superimposed, they have the CT angio superimposed. So all the data is superimposed on the same field. That robot recognizes it. And if I am a stupid surgeon and I am moving my knife or diathermy or something near the hepatic artery, it will stop. So this is something that is really be a game changer, because today when we are using robot and minimally invasive, etc., this is fascinating. Because this is a data frame. In the same data frame, you fit in your CT. In the same data frame, you put in your angiographic data. The map is there in front of you. And if you have fallen asleep and your instrument arm is going to tickle some artery or portal vein, it will stop. It won't allow you to do that because it will now sense and recognize the anatomy. Now that is a huge leap forward. This is a way, this is a very clever way where you can calculate blood loss in the operating field. Because simply by looking at the images and the color intensity, at the end of the operation, you can be told that how much is the intraoperative blood loss. And like always, surgeons are heading for more and more trouble. Because if you just have 4 cameras inside the operating theater, the working efficiency of a surgeon will come out like a report card. How much time you have taken? What was your movement? To do one anastomosis, how many movements did you need? If to do the anastomosis, you should have completed it through 60 movements, why did you require 80 movements? Are you becoming old? Is your hand tremoring? So at the end of every operation, an ergonomic efficiency report card of a surgeon is going to come out in the very near future. There is no surgeon who's going to come out of the operating theater and say, I am God's gift to surgery. Your software person will tell you you are actually very stupid. You are making many more moves than you ought to. So the days of claiming that everybody trying to be a hero is quickly getting over. If you want to be a hero, hurry up. So you will be measured. I know very little about the details of anesthesia, but what fascinates me regarding cardiac anesthesia right now is what you call the closed-loop anesthetic techniques. I really don't know how happy or sad you are with it, but to me, as a surgeon, there are points of interest that you are looking at parameters, you are looking at pharmacological agents, you are putting your endpoints, and this closed loop, depending upon the endpoints you have ascertained, whether it is sedation, whether it is analgesia, whether it is paralysis, neuromuscular paralysis, whether it is hemodynamic endpoints, The machines will go on working in the feedback loop. The question is, do you then have a control of the feedback loop is the question, or is the closed loop system going to override you? I don't know whether any of you have tried it, but this is now supposed to be the in thing. The in thing of machine controlled anesthesia now, closed loop delivery. I will probably await your judgment whether you're happy or sad with it. And somewhere based on this model, the Canadians came out with an idea which was called the Max Sleepy anesthetic system. You may have, I don't know whether you have tried it out or not. I'm very surprised the Canadians did it. They're a very conservative medical system. But Max Sleepy, where they have defined this closed loop endpoint run anesthetic systems, I'm told, internet hardly criticizes anybody. I'm told that they are fairly happy with it. Is it less error? Then robotic intubation. I mean, this is a very challenging concept. This is a robot intubating somewhere in, this is probably Johns Hopkins where they're trying it out. And they have a robot, they position it at the head end and believe that the robot is, this is a Kepler model, I think. This machine is called Kepler. This is a Kepler robotic model which is now able to intubate. It is always good to have it in a video. I will not risk it myself, not at this point of time. So, again, $1 million question. So, will all this gradually replace anesthetists? Well, so far, nobody has asked the question whether it will replace the surgeons or not. I think that is the next question which is coming. But probably, if you ask me today, the mandatory presence of an anesthetist for all sort of repetitive steps in the operating theater may be reducing. I'm not entirely sure. How is our domain doing regarding application of AI? We are really at some time ago, to about a year back, we used to be at number 2. Cardiology but a little bit of cardiac surgery was number 2 after radiology, because the highest application of AI obviously was in imaging. Was in radiology, we were at number 2. I see that in the last few months we have been overtaken. The psychiatrists are doing a lot of work. I don't know what psychiatrists are doing with AI really, but psychiatrists have become very busy with AI. Neurologists are doing better. So in this race for adoption of AI, from number 2, we have been pushed back to 4 or 5 right now. So obviously it's an interesting area, and like most things, China is leaps and bounds ahead of us. If you travel 30 kilometers north of Beijing, you will come to this hospital, which has just done away with 80% of their manpower, and it is said to be China's prototype AI hospital, where you will be greeted by a robot will take you to the bed, a robot will give you the medicines, and how much is the robot involved in rest of the clinical procedures, I'm not that sure. Now, this is all the good news with AI. Now, what is the bad news? The bad news is get ready for job losses, right? The world as we knew it will change. How much will it impact medicine? How much will it impact surgery? How much will it impact anesthesia? We are not that sure at the moment. Every repetitive, non-analytical area of work should be getting ready for a 30% job loss. When will it happen? In India, is the speed of adoption going to happen in the last half a decade, 1 decade? We are not sure. I still remember there used to be a few people outside my house who used to sit at a typewriting school. They used to, I don't know whether many of you may not have seen what a typewriter looks like. I used to have a typewriter when I used to write in school. So there were still 5 people way in, I think till about late 80s, they were going on. They were saying a typewriter will never become obsolete. Obviously, I don't see them anymore, right? So the bad news with AI is definitely going to come. Skill levels, requirement for actual physicality and skill will be delinked. And there will be a lot of churning. Yes, you may argue that we need more skills, different kind of skills, and very similar to eating, drinking, and going to the toilet. I think all of us today, if you see yourself, I perhaps don't, if you see yourself in the profession for anything more than the next decade, this is something like respiration. This is an area you have to know, full stop. And all our degrees, all our academic ornamentations will very shortly become completely irrelevant. Which stupid person is going to say today that an MD is more educated than an MBBS, a DM is more valuable than an MD? All that will become holy trash in 10 years' time. All this hierarchy of education will become sanctimonious nonsense. So you will be judged on your ability, your skill, and there will be only one endpoint, your familiarity with technology. Rest of it is immaterial, right? Get ready. AI today is committing loads of mistakes. I was hearing the gentleman, he said a lot of pertinent things. When a big, large language model makes a mistake, like when a doctor makes a mistake, what do we tell ourselves? It's a learning curve, right? So we are still learning, So yes, we make mistakes. AI makes buckets of mistakes. And the technical term, if you ever see LLM hallucinating, currently the fashionable word is hallucinating. It actually means it's a useless model. It's not good in this. It's making a lot of mistakes. They carry a lot of bias. You try using DeepSeek, ask DeepSeek anything to do with China, you will know what it is. And data security, what I think Dr. Maheshwari was saying, data security, take it from me. I know a fair bit about data security and encryption. Data security is just defined by one word, that is trash, absolute trash. Today, any class 7 or class 8 clever character can hack into any hospital's database and download the whole database in a server within 1 hour's time. So if you ever think you are in a data secure atmosphere, you might as well, this is a height of delusion. Data security is relative. It just depends how good the hacker is. It's a completely relative term. There is nothing called data security in today's world. Do we have Indian algorithms right now? Do we have Indian large language models? Actually, we don't. End of story, full stop. Why don't we have Indian LLM models, large language models? Simply because we do not own our own data. We have not owned our own data. To create a large language model is tremendously expensive in terms of data, in terms of money, in terms of power. To power ChatGPT, they require 2 nuclear power stations. If there were 2 large language model companies in Bangalore today, Bangalore will run out of water in a week's time. So much water is required to cool those servers and systems. And sometimes you listen to all this nationalistic hubris that, we are catching up with China doing all this. China is about 2 or 3 years behind USA. USA is definitely the market leader. China is at maximum 5 years behind USA. We are about 30 years behind China. So we are adopting, we are learning, we are applying, like the same we did for any other software. And this is just a table You can read it yourself in terms of patents, in terms of supercomputers, in terms of large language models that are developing. The end game is we are nowhere in comparison. We should just now start learning. So at the end of the day, we have to be hopeful. There is a lot of AI developmental activity happening all around us. Whether you want to be an entrepreneur, whether you want to be an original model developer, whether you want to apply it in your professional domains, or even if you want to write a love letter with it, whatever hell you want to do with it, please get on and start learning it. There is simply no other option. And organizations and hospitals, like big hospitals like us, or 3-4 other institutions in the city, has to seriously invest its own AI model, its own AI agent, its own AI chatbots. Exactly, it's not a world of difference with it. Exactly the same thing that you were doing with your Excel, the same thing that you were doing with your research, the same thing that you were doing with your statistical packages. The same activity has to be upskilled. The same activity has to be upscaled significantly. So amongst ourselves, if you want to stay in the business, it is like riding a cycle. You are either on the cycle or on the ground. There is no intermediate position for a cyclist. So similarly, if we want to be relevant to this profession, which is somewhat scientific, go home, pick up a book, subscribe to a course, because this is something which is absolutely essential. Thank you very much. If you have any questions, we'll answer. Eta hoega, sir. If you have any questions, I'm welcome to take it if it is within my understanding. Thank you.
Always this very, very nice and presentation as always. It's very much informative. So I just want to ask one thing. Artificial intelligence is created by the human intelligence. So what is the human intelligence and artificial intelligence stands as of now? I mean,
So all this because we have just created something which is I don't know. We have just created something which is intellectually fast. Why the hell do you take photographs with yourself on camera? There will be a law very shortly which will tell us that a human being should not look at an X-ray. Because apart from experience, you cannot compete with a machine as far as analytical visual activity is concerned. You cannot. Then all of us should be walking. Why do we ride a car? Because your speed of walking is 4 kilometers per hour. If your car is going at 60 kilometers per hour, it is dangerous. And so far, where is the problem? So far, in the first, second, third, fourth industrial revolution, every industrial revolution was replacing physical work by mechanized effort. This is the first industrial revolution where you are reducing average intellect by hiring. This industrial revolution is not about replacing physical work with mechanized. We have. It has been done. Now, where will we fit into the puzzle is the question. What is the next AI which is coming? Today you are looking at generative AI. The next AI which is coming is called HPI. It is called the general, they have named it very cleverly. Otherwise, it will shock the hell out of us. It is called general AI. How does generative AI differ from generative AI? Generative AI may be writing very nice pieces, giving me synopsis on material that existed. And this fellow is now capable of completely original thinking. As I was telling you, patterns, what is pattern? Say at the, God knows what, you are at the deeper and deeper and deeper and deeper levels of neural learning. No, it is not like analyzing where your Excel has gone from. We do not have the capacity to go to that level of neuronal analysis and find out where it is it right or not. So whatever it says, as somebody was saying, the AI models will have to validate. Fine. Supposing model AI, this agent is validated for medical statistics. Supposing it is, it will be beyond our capacity to go and question. Who will question? Do you know what to question? Where is the question? You can go back to your machine and recalculate the Kaplan-Meier calculation. But what the hell do we calculate over there? We don't even know what are we looking at. Our brains are not wired for it. There is the. So yes, let us be in humble acceptance of the fact this has happened. And let us not be sentimental that, humans will, fair enough, we will compose some songs, we will make some things, we will make some videos. It's already making very good videos. Two days back, I gave a 1.5-hour lecture on AI in Ramkrishna. And Maharaj was there, the last photograph I showed him was of Khani. And I told him, have you ever seen that photograph before? He said, no. I said, of course you haven't. That photograph was made by Rock. So it is there, people of your time. Now there is a bit of serious learning involved with it. You have to know what you want to do. You have to know what are the AI agents that are relevant to you. You have to know how can you work better through it, and how is it fitting in your profession. You have to. You have to. And there is no coding. You are not sitting down and learning some JavaScript, some this language and Fox Pro and all that. You just need to know how to navigate. And anybody who has a 10-year-old son or daughter at home, your best teacher will be that 10-year-old or 11-year-old. Sit with them, talk to them for at least half an hour a day. Within 1 week, you would have learned everything. They know much. Much.
In previous discussion, let's say taking echocardiography, the AI itself, ChatGPT itself answered that it augments the performance, but it does not abolish the manpower.
That's great. It is being very humble right now.
And sir, do you think that, as you predicted, that by 2030, 30% of the manpower will be slashed?
Look, manpower as you know it now.
Yeah.
Today, your HR world has a manpower definition. So the manpower as we now will be disrupted.
Maybe it will be distributed to other way, because for using the AI, the machine is still in it. Yeah. And do you think that this government should bring some regulations and laws to somewhat restrict use of AI?
The first thing is politicians should be replaced by AI. I think this intellectual capacity is far above now. It's a very interesting game. Let's see where we end up.
Yeah, we'll see where we go. Thank you, sir.
Excellent presentation, sir. Thank you very much, sir, for your invaluable time, inspiring words, and gracious presence. Actually, we are truly honored to have you with us today. Thank you very much, sir. We will move on our next session That is the AI-based hemodynamic model monitoring in cardiac anesthesia, the real-time prediction models, the hypotension prediction, the HPI, the smart fluid responsiveness tool by Dr. Shubhendu Sarkar, the senior cardiac anesthesiologist in Dishan Hospital present. Sir, stage is yours now.
important thing is, if you understand this cartoon, that a human, I can learn everything automatically, from that experience, can you learn? The AI says, yes, I can also learn from the past data with the help of machine learning. So here lies the trustability and the practical utilization of artificial intelligence in our situation. I'm not going to tell you anything about what is AI. I'm not going to tell you what is the discussion, what is the perspective over the entire medical fraternity. I'm very much focused about the existence of AI exactly in our clinical practice. The machine learning having the key concept of the different types of, one is a supervised, next in an unsupervised, and next in the reinforced learning. And this is in general the how AI works. Starting with a problem selection, then it goes to the data collection, it go to the model development, training validation, prepare a model assessment, and then the model deployment. This is usually for any type AI that works. The enhancing the data analysis and prediction, it can be a real-time data prediction, it can real-time data processing, instability early prediction, and prediction analytics for the shock and cardiac events. The decision support for the clinician is the treatment recommendation, optimizing fluid management, and automated alarm system. Now here comes, if you say, we really trust AI, if we can have the proper analysis of these three blue headings. One is a treatment recommendation. Number two is optimizing your fluid management. And next is automated alarm system. If it is not going to help us, actually in our critical cardiac intensive care area, AI has not that much of effect. This is the machine learning model. You know, this is the different types of model. Example, we have the deep mind health. We have the predict clinical deterioration by integrating real-time ICU data. These are the different machine learning model that works. And this is a sepsis detection model. This is how the decision support system and the precision intervention. আমার মনে হয় এগুলোকে ডেসক্রাইব করে আননেসেসারি এখন সময়টা নষ্ট করা বা জিনিসটাকে আরো কমপ্লিকেট করার কোনো মানে হয় না। এমনি আমরা প্রায় 1 ঘন্টা লেটে যাচ্ছি। This is an image-based non-invasive hemodynamic assessment. Whenever you do this transthoracic echocardiography assessment, now you know majority of the machines has become and impregnated with your artificial intelligence. This is actually how this caption health, this is one, how it works. Audio ta nei na?
Or patient indications. Sarah will start with a parasternal long axis view. She uses the diagram in the lower right to position the transducer. Above that is a reference image that shows her what the current view she's scanning for should look like. Following the guidance prompts at the top, Sarah makes specific transducer movements to optimize the image. On the left, the quality meter tells her how close she is to capturing a diagnostic quality image. As Sarah gets closer to the optimal view, the meter rises. Once the software detects a diagnostic quality image, the meter turns green and the clip is automatically recorded without having to press any buttons. Next, she moves to the apical 4 and the apical 2 chamber views. She follows the real-time guidance and continues making fine movements to enhance the image. You'll notice that with the addition of multiple views, the ejection fraction measurement displays automatically. Caption AI continuously keeps track of the best images seen while scanning, so at any point, Sarah can choose Save Best Clip to capture the best 2-second clip and move on. The report page shows the final ejection fraction measurement utilizing all 3 views, mapped to the corresponding clinical guidelines for left ventricular function and a confidence estimate.
কিছু বোঝা গেল? Whenever you are using this AI, for every view, this software is actually calculating your 5 best movements. And among these 5 best movements, it picks the best one and it automatically gets restored. Now, The machine next come, when I was showing this development data, it actually need to compare before it comments, it's really in a normal level. So you need to fit with the patient data and everything. So these are the all expected things where we'll say if the value is within these limits, the patient is going to be a normal one. So for every your precision movements, you are liking or not, for every precision of your movements, it detects the best 5 movements of your, and among these best 5, it creates the maximum which was in best. It is something like calculating the intermittent thermodilution output. So that gives you the entire value of the ejection fraction of all these 4 views. This is actually the basic way how the AI helps us in cardiac intensive care. So again, I'm telling you, I'm not here to discuss anything about what is happening, but in what we actually practice as a specialized, as a super specialized, the area where we work, it helps like this. Okay. So this is we are having the same way for this non-invasive one. We have this Hypotech registry, that is an AI prediction of the hypotension prediction index. This is a study period of 2001 to 2021-22, almost 749 high-risk surgical patients, and they have used this Acumen hypotension prediction index, that is you all know by the Edward Life Science, and uses the predictive algorithm and shifts the intraoperative management from the reactive to the proactive. These are the parameters analyzed from all the 1 to 7, and the purpose is obviously to make a hemodynamic stability of the patient. And these are the all registry finding of this UP Hypotech study. But the most important thing of this study that came out is the alarm fatigue is a significant concern, and about 8 to 10% cases, there is a desensitization to the alarms in a widespread issue. And probably that correlates with our maximum crash that is happening in the intensive care is something after the 2 o'clock in the night or something like that, or between in the early morning. So these are the 2 important things. So now here the important thing comes, if it correlates this alarm fatigue, and that gives one of the extra solution by the artificial intelligence by this hypotension predictor index. That is the previous study what I have showed. These are the parameter analyzed by the HPI Acumen, that is a hypotension prediction index, and it gives us the real value this patient is going to crash. So I'm going a bit fast, that AI supported clinical decision making, the challenges and the limitations. The number 1 is the quality of the data is a paramount. Training machine learning models until and unless your first point is solved, your AI is not going to work. Next is the challenges from the potential bias and the inaccuracies on the training data, impact on the algorithm performance and the diverse patient population, lack of the interpretability in complex neural networks, challenges in understanding the model conclusion, and challenges in incorporating AI-driven hemodynamic monitoring system into the healthcare, the compatibility issues and the need to seamless data exchange between the system, and established and effective collaborations between the healthcare professional and AI system. Balancing the AI as an adjunct to the clinical judgment rather than the replacement. So these are the all 8 কতটুকু বোঝাতে পারলাম জানি না, খুবই ফার্স্ট বলে গেলাম, but these are the all 8 basic limitations of artificial intelligence and hemodynamic monitoring. Regarding the ethical consideration, একটা পোর্শন হয়তো ডিসকাশন হচ্ছিল, that is an ethical concern in AI and healthcare. This is one of the prime importance right now, that the use of the AI in healthcare raises the ethical concern. You are particularly regarding the patient privacy, patient consent, and the responsible handling of the sensitive medical data. This is one of an extremely important and the first point hindrance of the AI implementation in a regular basis. The next one is obviously need a clear guideline, dynamic natures of our hemodynamic parameters. The number 3, we always suggest these dynamic natures. I don't know how many permutation and combination AI can really give us with so many of the dynamic variability. The challenges is a real-time prediction and the validation is obviously needed. So future directions are this, and enhance the transparency in AI model. Until and unless you cannot do it, you cannot implement it, because this is a real-time challenge. Implementing an AI in a transparent way, in an ethical concern, we can discuss hell of a lot. We can discuss a lot of things about the 3D, 4D, 5D, ZD, TOE analysis. We can discuss a lot of things. We can discuss a lot of download papers and other, but the most important thing is its actual implementation in our cardiac critical care. That's a real concern. And the first step is whether your entire system is transparent and ethically acceptable to this patient population. That is the most important. I don't think there are only not more than 50% patient whom you actually convince about this AI implementations. If you go on saying that your entire thing will be AI based and we are going to diagnose and make your treatment vis-a-vis with the clinician with an AI, it's really going to be very tough. Probably in coming 10, 15, 20 years is going to implement, but this ethical and transparency is one of the most important hindrance, what I personally think in our specialty. The importance of the AI in clinical decision making. Advanced signal processing technique and predictive analysis of the hemodynamic monitoring, improving the patient safety, need for the regulatory framework, and this. The last part of my presentation, I'll take another 3 to 4 minutes time and then we'll sign off. We all know this device. This is the hypotension prediction index. That is an Acumen software where the surgically patient more than 65 years of the age, hypotension is very common, almost 83%, and lasted over 20 minutes in 28% of patients. Every 5 millimeter of mercury below the threshold of 65, it increases the odds of the adverse event, and more the time below the threshold, further increases the adverse event. Even 1 minute of hypotension below 50 millimeter of mercury is associated with an extremely higher risk. These are the real scenario of cardiac critical care. And that's why you can say the need of AI is really the day of need for us. Acumen shoot with an hypotension prediction index software, with a sensor and with an analytical software. The entire hypotension prediction index software, the Acumen, is comprises with these 3 pillars. We commonly call it an Acumen shoot. The key points I'm not going to discuss. This is the software. All this hypotension prediction index and other is not going to discuss much. The parameter alerts and the secondary screen. These are the different screens that pops up. And the IQ sensor unlocks the intelligent decision support for hemodynamic management. And this is how the thing goes on working. We need to zero the waveforms and other, something like this, and go on calculating. This is the Acumen shoot. We have connected the Acumen shoot and how we are going to use it. These are the different screen that goes on. This is how the fluid responsiveness with it, we need to incorporate all the data. We need to incorporate all the inotrope, vasodilator support. Even the patient is on pump, the cross-clamp time, warming, cardioplegia, everything is there. So if you want to use it, you can really use it from the intraoperative period. That helps us. So what are the parameters? HPI parameters is an index with a value of 0 to 100. The higher value having the greater likeliness of the sooner, and the lesser is less sooner. And HPI secondary screen allows screening to understand the continuous hemodynamic parameters. And we have these 2 important data, probably on আজকে সকালবেলা হয়তো অনেকবার আলোচনা হয়েছে, the DPDT and the EA-dyne. This DPDT is the contractility parameter, and EA-dyne, that is an afterload. We know that starting from our maximal invasive monitoring to the minimal invasive monitoring to the non-invasive monitoring, to me there are almost 48 to 52 datas or the parameters depending upon different companies and depending upon different parameters. Suppose in the PICO technology we have this global end-diastolic volume, intrathoracic thermal volume, we have pulmonary vascular permeability index, we have all these extravascular lung waters and other. But here the 2 new thing parameters, how the in general, grossly, rather not going to the details of the crux of the thing, this DPDT and EA-dyne is going to help us in predicting the hypotension in coming half an hour or 20 minutes to 30 minutes with this contractility analysis and the afterload analysis. So this is how does algorithm works. You know, this is how this is getting calculated. Probably we need this pulse pressure variation and the stroke volume variation. See, Acumen should is actually based on this APCO algorithm is the basic one. So once your machine is compatible with the APCO algorithm, you are going to get the stroke volume variation and the pulse pressure variation. And from that, the intercalculation comes. And it's how tell us what is the interaction with the large vessels, evidence with the ventricular contractility. It suggests whether if the patient who is fluid responsive will also increase the arterial pressure to the fluid administration, optimal cut-off mean arterial pressure, and may also use to titrate the vasopressor therapy, whether you are going to start the vasopressor for particularly this predicting hypotension. This is how the EA9, that is the dynamic arterial elastance, works. And you can see if it is less than 0.94, may predict mean arterial pressure drops in response to the decreasing vasopressure. So it's not only that analyzing you are going to start for reading the titrating or reducing the doses also, this is going to help us. So these are the all key points. I'm not going to tell you much because limitations of arterial DAPT, your patient is having severe aortic stenosis, your patient is severely vasoplegic, cardioplegia এমন ভাবে দেওয়া হয়েছে বা post operative patient is having severe vasodilatation or at the beginning of the sepsis and then undefiled state. These are all the different situations where we cannot actually use the DPDT, that is an resistance. So in general, যদি আমরা জিনিসটাকে আলোচনা করি, for every incidence, this is my last sentence for this presentation, there is a 2.6 million permutation combination. And this 2.6 million permutation combinations within Acumen should, it comes to a level of 23 most predictive features. This what Acumen should does for us. Don't ask me the validity. Don't ask me about its utilization. Don't ask me about the ethical consideration, transparency, all the hindrance. That was my first part of presentation, that what is AI is actually in cardiac critical care right now. But if you say what is existing, what the machines, I have a fortune to use it for few of my patients, this is the step ladder pattern from 2.6 millions for every incidence permutation combination. It comes down to the 23 most predictive value, and then it helps us to go on identifying this patient is going to have hypotension in some period, or this patient is stable in my opinion, but if its dyne is okay, we can easily start tapering the vasopressure. So this is the lab summaries and other. Thank you very much. সময় মতো শেষ করেছি, খুব বেশি সময় নিইনি। আচ্ছা, এই আসতে হবে না, আসছি এক সেকেন্ড একটু অ্যানাউন্স করে যাই। ইন্ডিয়ান সোসাইটি অফ ইন্টেন্সিভ কেয়ার অ্যান্ড পেরিঅপারেটিভ মেডিসিন, we invented or established their West Bengal state branch in month of March 2025. We are going to have our second national conference. দেবদীপ, আমার ব্যাগটা একটু দিবি, নীল ব্যাগটা। সেকেন্ড ন্যাশনাল কনফারেন্স ইন কলকাতা 31st of October, 1st আর 2nd November। আরেকটার সবাইকে ইনভাইট করা থাকলো। হোটেল হিন্দুস্তান ইন্টারন্যাশনালে হচ্ছে 31st আর 1st আমাদের প্রোগ্রাম কনফারেন্স, অ্যান্ড 2nd November ইজ আওয়ার ওয়ার্কশপ। আমাদের একটা ওয়ার্কশপ বিএম বিড়লাতেই হচ্ছে, হ্যাঁ, ইকোকার্ডিওগ্রাফির, তো সেখানে অবশ্যই আসবো। এখন তো বাজারে এটাই খাচ্ছে লোকে, সুতরাং এটা তো থাকবেই। আর I'll request Dr. Ravi and Dr. Mona Lisa and Dr. Praveer, please to come on the stage for few seconds so that on behalf of the society, I can hand over our brochure conference to you all. It's on behalf of our society. Thank you. I'll request all the active members, please come and join. আয়ারটাতে আসতে ভয় লাগে, সবাই এত পড়াশোনা করে আর আমার তো এই খুব খারাপ অবস্থা। তো যাই হোক, তো প্লিজ অন বিহাফ অফ আওয়ার সোসাইটি প্লিজ কাম এন্ড জয়েন দ্য প্রোগ্রাম। আর আমাদের we are keeping one hall only for the PGs for 2 days. একটু তোমরা ইনফরমেশন পাঠিয়ে দিও সবাইকে, ঠিক আছে? মোস্ট ওয়েলকাম, থ্যাংক ইউ।
Thank you very much, sir, because of that excellent presentation, the crisp and to the point. Thank you, sir, for the invitation. We'll definitely go into that conference and make the conference successful. Proceeding to our next, the last lecture of this CME, AI and the Precision Anesthesia Model, Intraoperative Challenges and AI Assistance. The speaker is none other than Abhinandan Mondol, Senior Cardiac Anesthesiologist, Apollo Multispecialty Hospital, Kolkata. Abhinandan, please start your presentation. Thank you.
Sorry. Please. Thank you so much. I'll try not to bore you all. Okay. So, switch on off the light. Wait a second. Just a minute. टाइप से लेके जाबे ओके 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 ठीक है লাগিয়ে দিয়েছি আসবে ওকে না না দেখছি দেখছি thank you so much. Sorry for delay. So what is the scope of this session? What we'll discuss? What is the concept of precision in anesthesia and its relevance in cardiac anesthesia, and how it becomes a challenge intraoperatively, and how is AI is going to help. So I'll just keep it very straight. So this is a precision medicine future of anesthesia. This is a model of precision medicine, precision anesthesia in the year of 2050. What it's going to be? It's a Kuo et al. 2023. It came in the anesthesia analgesia. So the precision cardiac anesthesia, what it means? It means a personalized approach during preoperative planning. That means one size fits for all. It's nothing like that. That every patient is different, so we'll have to personalize these things. So selection and stratification of the intervention, that is anesthesia analgesia regimen, anticoagulation, circulatory assistance, hemodynamic optimization, and mechanical ventilation. And also we need to predict the incidence and the severity of any complication. For example, postoperative atrial fibrillation, low cardiac output syndrome, vasoplegia syndrome, ischemia reperfusion injury, and so etc. So we'll focus on this slide and we'll go on. So field of anesthesia has considerably evolved in the recent years. So these are innovations in drugs, monitors, and equipments, and also the patient safety. And what are the new technologies that we have? There is a three things that we have right now. Is artificial intelligence, internet of medical things and omics. Artificial intelligence, already we have discussed, will go straight forward to the Internet of Medical Things. So what is this Internet of Medical Things? It is our digital health that we use every day, that the smartwatch that we use for our regular heart rate monitoring, your blood pressure, your ECG monitoring, your blood pressure monitoring, and also your blood sugar. Now you have every sensors is also connected with your mobile app, so that your data is also being shared to the mobile app, and through that mobile app your AI is getting the input for that. So all these digital, this patient, suppose this patient has a wearable device, and this data and all these heart rate monitoring sensors and your blood pressure sensors, all these being data is going to your Internet of Things cloud. Okay, so this Internet of Things cloud, there is a huge storage of your data, and that data is being analyzed, and this entire part is done by AI. So this will give you the input for the to the doctor, that how your normal, what is your normal blood pressure ranges, what is your normal heart rate ranges. Because as a cardiac anesthesiologist in a pre-operative anesthetic clinic, hardly you know a single reading of your patient. That is a single blood pressure reading, single heart rate reading, that will not give you the entire scenario of the patient. What is the patient, what is the normal blood pressure of the patient, what is the normal range of the heart rate of the patient, what is the normal range of your every other details that being shared by the online. So let's go to the next thing, that is omics. What is omics? There is a multiple omics that we deal on. That is, right now there is a genomics, epigenomics, transcriptomics, proteomics, and metabolomics. What is the do by genomics? It deals with every genetic data of you. That is your pharmacogenomic data. Number two is epigenomics. It is for the gene expression. Transcriptomics, it is for the RNAs and microRNAs. Proteomics, all the proteins that being produced by your body. And also the metabolomics, all the metabolic products that being delivered to you. What exactly it is? Suppose it's a pharmacogenomics in genetic factors. Is cytochrome P450 that we already know that this, if you have any genetic polymorphism, the isoproterenol and opiates metabolism gets different. If you have any mutation in BCHE gene, you have a pseudocholinesterase deficiency. It slows the metabolism of certain drugs. And if you have any mutation in the opioid and versatile anesthetic receptors, it will also influence the effects of your anesthetic drugs. So all this information goes via the AIs to your anesthesiologist. So what are the relevant omics in cardiac anesthesia? Suppose there is a genomic screening of your clopidogrel resistance. If you have any already you have any mutation in your cytochrome P2C19 or statin related myopathy risk, that is SLCO1B1, identification of any arrhythmia syndrome, you have a long QT or Brugada syndrome. If you have any pharmacogenomic tailoring of warfarin, suppose you have any abnormal metabolism of warfarin, it will actually tell you what should be your ideal warfarin dose for your particular INR range. And also it will predict your acute kidney injury or post-operative atrial fibrillation, that I am coming next. And also the epigenetic markers, whether you will have a more risk of a prolonged ICU stay, opioid sensitivity, and delirium susceptibility. So you can just tell those things pre-operatively to the patient and the patient parties. So these are the these mRNAs are already there. This MIR1, this downregulation, MIR7AB overexpression, all these mRNAs will tell you whether your cardiomyocytes survival and apoptosis pathway is on or not. This is the post-CABG. It will tell you whether the post-operative cardiac troponin release will increase or not, whether the patients have a more chance of post-operative MI or post-CABG MI. So these things are done by your transcriptomics. That is, for example, there's microRNA 1. If this expression is increased after CABG, it has a positive correlation with cardiac troponin I. And this is a microRNA 126. Its expression is increased after CABG. It is associated with your uric acid level. So this microRNA 133, this expression is increased after CABG. It is associated with cardiac troponin T and reflected the extent of MI. And this expression of microRNA 199A, if this expression is decreased in CABG, it has a positive correlation with EF and negative correlation with MES. So there is a biomarker to identify post-cardiac surgery myocardial infarction. So similarly, these microRNAs will also tell you how to deal with your postoperative atrial fibrillation, whether you have more risk of postoperative atrial fibrillation or you have less risk. So this is a new biomarker study that has come up from the Journal of JTCVS. It's a biomarker analysis for cardiac surgery associated acute kidney injury in patients without cardiac arrhythmia. So they have studied 36 cytokines and chemokines for the study. So they have come up with these three parameters, that is haptoglobin, interleukin 1 RA, and myoglobin, whose level after 4 hours, within 4 hours, if it is increased, then the more chance of acute kidney injury. So by this image, we can you can think it right that we are talking about human digital twin. So what is this human digital twin? So this is suppose if this is you have this your physical format, and this physical form will have a similar digital twin. So what that similar digital twin will have, it will have a continuous sensor data, your clinical data, and your demographic and genetic data. So they will form a digital twin of you, and also it will continuously gets updated from your body as well. So it will also tell you the prediction, the how you will behave to the particular surgery and particular intervention. So it will tell you whether you have a particular disease risk assessment, whether the particular treatment is recommended for you, and whether your lifestyle requires a certain prevention or any recommendation. So human digital twin requires your electronic medical records and your IOMT value, and this will tell the artificial intelligence, and it will provide two types of twins, that is Najwell twin and a prevention sick twin. So what is Najwell twin in cardiac anesthesia? It is a preoperative optimization of relatively stable cardiac patients. That means this is to be done in case of elective cardiac surgery patients. So it keeps low risk patients optimized to avoid intra-op deterioration. So what are the areas that we can use it in a case of prehabilitation, in a case of behavioral nudges and patient education? So in a prehabilitation, AI guided exercise, diet, and your medication adherence. In behavioral nudges, the patients to continue beta blockers, stop smoking, your anticoagulants and dietary sodium restriction, patient education, digital coaching, and procedure expectations and recovery. What is prevention sick twin in cardiac anesthesia? This is for the high risk patients, for the severe AS and LV dysfunction, for example. So it predicts the decompensation in high risk patients and enable early intervention. So what are the areas and application? Suppose intraoperative prediction, AI detects pattern suggesting imminent hypotension, myocardial ischemia, or arrhythmia using human digital twin, like linked to live TE, arterial waveform, and your labs. It will tell you the exact ventilation strategy that your patient should have. AI helps to avoid RV failure in pulmonary hypertension via human digital twin informed lung protective settings, and your drug response modeling as well. Whether the patient is having severe AS, so therefore there is a more chance of hypotension with propofol, for example. Fluid and inotrope management is a closed loop system, suggests optimum inotrope and vasopressor strategy based on your afterload and preload status from the human digital twin that already Suvendu sir has already mentioned. So precision cardiac anesthesia aims to tailor cardiac anesthetic care to the individual patient's physiology, genetics, and procedural demands. But it is technically very challenging. So what are the challenges that we face? Number one, there is an intraoperative physiological variability. There is a rapid hemodynamic fluctuations. During sternotomy, bypass initiation, cross clamp, reperfusion, there is various steps of cardiac surgery. Each and every steps require various targets. The targets of your anesthesia is completely different in various stages. So response of drugs also can change minute to minute. So making real-time individualization is difficult. Number two, limited real-time data integration. Multiple monitors. You have multiple monitors to attend with. T, arterial line, Bs, NIRS, cardiac output. They provide data, but no unified platform is yet available for real-time precision decision making. And it is difficult to synthesize multi-source data dynamically at bedside. Number three, variability in the patient pharmacogenomics. You do not know the exact genetic study of your patient yet. It is yet to be come in future, but right now you don't have. Genetic differences affect responses to anesthetic agent. There is opioid, muscle relaxants. So lack of rapid point of care genomic testing limits real-time tailoring. Number four, incomplete models of goal-directed therapy. So fluid vasopressor and inotrope management often follow population-based targets. And those population studies has been done mostly on the Western population. Though not all patients fit the mean individual optimum map, cardiac output SVR is unknown intraoperatively. What is actual optimum for that patient is actually unknown. So TE interpretation variability. Precision depends on accurate dynamic interpretation of TE, and operator skill and subjective variation can affect clinical decision. So this has been already discussed details. In algorithm and AI limitation, AI and closed loop systems still under development or validation, not yet widely deployed or trusted for autonomous drug delivery or decision support, especially in cardiac anesthesia. Dynamic surgical environment. Your precision must adapt to unplanned intraoperative changes. For example, you are going for minimally invasive to suddenly the surgeon decided to open it up. So unexpected surgical duration. Number 8 is resource and team limitation. Full precision approach requires expert team coordination, advanced technologies, that is real-time omics or AI systems. These are not available in all centers. ECMO or CPB induced alteration. Suddenly patient requires a CPB on ECMO. This altered the drug pharmacokinetics, metabolism and temperature. So this makes drug titration more difficult. Now number 10, ethical and medical legal concerns. So risk of over-reliance on precision models without robust evidence may delay decision in critical moments if algorithm-driven suggestions contradict clinical intuitions. So what are the AI solutions that we have? Number one, all these solutions, let me say it very clearly, all these solutions are not yet available, but yet to be available. So number one, real-time multimodal data integration. So AI can synthesize inputs from TE machine, your BIS monitor, your NIRS, your cardiac monitor, your hemodynamic monitor, etc. They convert raw data into actionable insight, whether the patient is having hypoperfusion or any hypovolemia or something like that. The predictive analytics uses historical and live data to forecast instability. There is hypotension and arrhythmia. It anticipates critical events before they occur, just like your HPI. Personalized drug dosing, there is closed loop system. AI-driven system can auto-titrate anesthetics, vasopressor, inotropes based on real-time feedback from patient parameters. But this is still these things is not validated in cardiac anesthesia settings. TE interpretation support. AI can assist with automated image interpretation, detects valve motion abnormalities, valvular lesion, and ejection fraction changes. And it also reduces your inter-observer variations. So intraoperative decision support system, it provides evidence-based recommendation. What are the guidelines available? That will make you available at that moment of time. Helps in fluid, inotrope, and ventilation strategies tailored to current status. Number 6, AI-powered genomic integration. Rapid bedside, it is a future thing that is going to come. Rapid bedside genotyping and AI will give you the exact guide how much drug you are susceptible to a particular drug or not. Pharmacogenomic guided drug selection. It tailors induction, maintenance, and analgesia. Adaptive learning system. It will continuously learn from your institutional patient-specific data. So more the days come, more the AIs will evolve itself and improve performance in each case. AI-assisted team coordination. AI will assist you to how to your synchronization between your anesthesia, surgery, and perfusion teams, and it improves the response time during emergencies. Enhanced simulation and training. AI and VR will real-time intraoperative scenario training. So this is a very important application for your AI. It improves the clinician preparedness, but for rare but critical events. Ethical guardrails and error detection. AI flags unsafe trends, deviation from guidelines. It enhances patient safety and medical legal protection. So for the take-home message, precision anesthesia intraoperatively is limited by data, complexity, physiological instability, and technological gaps, requiring ongoing adaptation and clinical judgment. But AI acts as a real-time co-pilot. It's not your pilot, but it's a co-pilot, integrating data, predicting events, and recommending tailored action, transforming challenges into opportunities in precision cardiac anesthesia. Thank you for your patient hearing. Thank you.
Vinodhan, excellent presentation. That was a really to the point, very short and crisp presentation. Thank you very much. Thank you.
So all the senior faculty members, presenter, dear colleagues and learners, on behalf of WB ACTA, I want to extend my heartfelt gratitude to each one of you for making this event quite successful, this futuristic program, the brainchild of Dr. Mona Lisa and team. So, a big round of applause. And I want to thank Dr. Pravir, Dr. Rashmi and team of BM Builder for hosting us, for nice arrangement and overall round nice arrangement. And just want to thank all the participants, all the senior faculty members who made this complicated and advanced technology-based topic to the reach of all of us to understand it better, to get ready for the future. So this is very important topic and coming up to change our practice in day-to-day life. And I want to thank all the technical staff who just made it possible to connect us with even the speakers with abroad and on Zoom and all the support. And thank you, everyone.